Okay, so welcome everybody. My name is Marko Lončar, and I'm professor of electrical engineering and applied physics at Harvard. And with me, I have CJ, student of mine. And CJ, you want to say a few words about yourself?
Yeah, I'm a 6th-year student working with Marko. Yeah, that's about it.
Perfect. And we are members of Center for Quantum Networks. And in particular, in our group, we do a lot of work in integrated photonics with applications in quantum and classical communication. And so this is sort of this presentation that's kind of is focused on integrated photonics platforms of quantum networks is kind of quite tightly related to what we do. But we, CJ and I decided to go for somewhat pedagogical, maybe overview of field of integrated photonics, with caveat that that's actually a pretty large field and it's impossible to cover everything in a short period of time. So we'll see how much we go. Maybe just a little bit of historic perspective. Photonics as a discipline didn't start the invention of lasers and optical fibers, and we'll say a little more words about it in a few slides. But basically, a lot of photonics, you can think of photonics as category subfield of electromagnetism, and broadly, and then also subfield of optics, which is essentially governed by Maxwell's equations, and we are listing them here that basically describe propagation of electromagnetic wave, and therefore also light in free space and in medium. And so Maxwell kind of basically unified electricity and magnetism to kind of derive these equations, and that they can describe, as I mentioned, propagation of electromagnetic waves and thereby also propagation of light in free space and medium. And all was good till actually it turned out that people couldn't quite use this theory to explain some physical phenomena, namely emission for a black body, right? Especially black body radiation spectra. So basically, Maxwell's equation assumed that light is a wave, but this kind of property of light was not sufficient to describe emission from black body. And that's when Max Planck postulated that basically maybe light can be thought of also as a particle, and using this kind of idea and describing light in terms of particles of light, photons with energy, as listed here, he was able to kind of describe this the experimental observation of black body radiation. And so now this was the first time that photon was introduced, which and then broadly speaking, going back to photonics, is a discipline where photons are used as information carriers in various information technology systems, as opposed to electronics, where electrons are used as information carriers. So here, basically, this was kind of birth of the photon, and furthermore, Einstein then extended these ideas and used this to describe interaction between light and matter, namely emission and absorption of light. And so what's illustrated here is shows how basically atom, when it's excited, and here excitation of an atom is indicated by this kind of electron cloud that is moving around. Atom basically can then relax and emit photon, or atom, as shown here, you guys can see my cursor, right? I assume the answer is yes. Alternatively, atom can absorb photon, and then atom becomes excited, electrons become excited, and this is the concept of absorption. And of course, stimulated emission happens when actually you have photon incident and excited atoms in excited state that then can generate two photons that are identical. So this is stimulated emission that's used to realize lasers. And throughout this presentation, we'll talk a lot about absorption, stimulated emission, spontaneous emission, both when we discuss classical and quantum devices. Though actually, strictly speaking, all light emitting devices are quantum, because photon is quantum object. So everything here is quantum, really. Okay, And then many years later, really when the modern field of photonics started was when basically first semiconductor laser dye was invented in 1962. And before that was also lasers. And then in 1966, when optical fibers were used to transmit optical signals across long distances, this is really when this kind of field of photonics was born, where, as I said, photons are used to carry information. In this case, across long distances, but you will see this is a very powerful concept that allows us to carry information even at short distances. With invention of lasers, people were able to hit matter materials with ever stronger intensities of light, and therefore novel phenomena started emerging, namely in optical nonlinearities. And we'll talk a lot more about this in the context of photon generation processes. CJ is going to talk about it at great length. Well, basically, these are at very high intensities, so optical pulses of continuous wave light. Basically, you cannot assume the medium is linear, and you need to take into account the fact that light may, generate new colors of light, essentially. These kind of the birth of both lasers and optical fiber has really revolutionized information technology, classic information technology. As we know right now, probably my video comes to you, not probably, definitely comes to you via optical fiber, because optical fibers are the lowest loss communication channels known to humans, and therefore basically when we need to send information across long distances, we typically use optical fibers. So what this map shows, brightness shows basically number of bits per second that are being communicated. This is Facebook connectivity map. So this doesn't take into account all other networks that are out there. And what you can see underneath the oceans are actually optical fibers that carry information between continents with very, very low loss. So that's just kind of, you may think that that computation and data lives in the cloud, but in reality, most the data spends a lot of time under the sea at the bottom of the ocean, where it's being carried by optical fibers. So optical communications really has enabled this kind of long distance connectivity, as just illustrated here, which is basically optical fibers form the backbone of internet, and they are powered by various integrated photonics components. We'll talk a little more about this later. But actually, optical technology, optical connectivity is used not only to bridge large distances, but also to, for example, connect computers in data centers, different computers in the same rack, or even different chips on the same motherboard in these data centers being connected with light, because this is the most efficient way to send information, and also at very, very high rate. The issue today that we are facing is that basically due to because everything is in the cloud, including this winter school, essentially the demand on data center infrastructure and kind of broadly speaking information technology infrastructure is huge. So, and that becomes non-trivial consumer electricity. For example, already several years ago, data center have consumed more than 10% of total electricity produced worldwide, and that actually trend is growing with especially with AI, advancement of AI essentially. So much of this energy is actually being used is also used in all data center was burned on shuttling information via electrical wires. And if you have metal, then you have ohmic losses. It's like your toaster back home in your house, in your kitchen. Like if you send electricity through electrical wire, you generate a lot of heat. And so that's not a very efficient way to just send information. So that's why people started actually using optical communication channels to send information even shorter distances. And even 5G and 6G, a lot of these actual technologies rely on optical connectivity. And this was actually discussed in one of the other lectures that we heard, but basically summarizes how basically optical connectivity, optical fiber networks are used to bridge distances long and short, essentially. And the simplest way to think about this optical communication channel, optical link, is essentially following. You have some sort of electronic computer, some information that sits in electronics domain, because most of our computers, almost all of them today, are at least electronics based. So information sits in electronic domain, and then in order to send information via optical channel, via optical carrier, you need to turn, for example, light emitting diode on off as bits of ones and zeros come that you want to transmit. You have a bit stream of ones and zeros. You can turn diode on and off, and that sends essentially optical bit stream. On the other end, of course, you need to receive this information and convert it back to electronics. For that, you use photodetectors. And so these are very well developed classical components. The problem, just for the sake of completeness, the problem with this approach, where you directly modulate a laser diode, for example, is that the speed with which you can do is limited by the physics, semiconductor physics of a light laser diode, essentially. So you cannot go very, very fast, which is why most modern communication systems that rely on very high data rates, exceeding maybe several gigahertz, gigabaud, rely on sort of externally modulated optical signals. So basically what you have laser that's always on, as shown here, and then you have device that we will call modulator that basically takes electrical signals and impart these electrical bit stream onto laser optical carrier, so onto this laser light. Then light propagates via optical fiber, and on the other end gets received and converted to electrical signal, where you can analyze it with electrical computer. So we'll talk a little bit about process of modulation, because these modulators that are based on interferometers are actually extremely powerful components. They're used not only to send data, but actually it can be used to build optical computers and quantum computers as well. And so this kind of technological drive or technological need for optical communications have really resulted in a boom in the field of integrated photonics. And with kind of advancement of integrated photonics, many other disciplines that use light could also be significantly positively impacted. In particular, for interest to this school, is optical computing, or computing broadly speaking, where light can be used photons can be used either as qubits, so they can be used to do calculation, or they could be used to transmit information in the context of quantum networks, quantum communication. Other interesting kind of technology that rely on light are sensing and machine vision, like in the case of LiDAR, AR, VR applications, and so on and so forth. For us, in our center, basically, we're very much interested in pushing the limits of this optical communication technology, where the information, in this case, quantum information, is carried across distances long and short again, but at one photon at a time, essentially. So we are interested in exploiting the quantum nature of photon so that communication can be very, very secure. And for that, and I think there was discussion about this in previous lectures, but just briefly, essentially, that requires that demands a lot more from photonics component than classical communication system. In classical communication system, you can tolerate some amount of loss because you can always amplify the signal using, for example, erbium doped fiber amplifiers. But in the case of quantum signals, when the information is carried with single photon, basically this is impossible for the reasons that ultimately makes this quantum communication channel secure, which is the fact that quantum information cannot be copied, cannot be cloned. So therefore, great care needs to be taken for these photons not to be lost while they propagate at distances. And so in order to kind of realize this dream of secure quantum internet that would be also ideally end coherent, which would allow you to load one kind of to distribute entanglement across continent, for example, or across planet eventually, hopefully, you really need many of these components, including quantum repeaters, quantum transducers, and whatnot, to be excellent. So we're going to briefly talk about devices that can enable this, and we're not going to so much focus on quantum repeaters because this is being discussed in other seminars. So So basically, in introduction, maybe CJ can take some of these slides, and she's, we'll talk a little bit about why photons are interesting as a flying cube. Actually, CJ, want to take this slide and the next few slides? I can just
absolutely. I am ready.
Advance it. Yep, go for it.
Yeah.
I can advance it for you, and then you can take over later.
Hello. Can you see my slides now?
Okay. Yep.
Okay. Give me a sec. Yeah. Okay. Okay. So yeah, after the very broad overview of fiber optics and communications networks that Marko has kindly provided, let's go over kind of what we're going to be talking about for kind of this next subsection. Basically, I'll just recap what makes a quantum network really quickly. I'll get like I'll really break it down like kind of components and then functions and component style. And then it's probably stuff that you've already seen. And then we'll talk a little bit about how that relates to photonic integrated circuits. And also let's get, and then at the end of it, we'll spend some time having you guys think a little bit about just knowing nothing, what you think is a good platform for photonic integrated circuits. And basically the thing to keep in mind throughout this entire talk is there are going to be a lot of materials, names of materials that you'll hear throughout this talk. Something to keep in mind would be trying to evaluate what, in your opinion, would make a good integrated photonic platform for quantum networks specifically. So first of all, just a really quick recap of what makes a quantum network. So of course you need some nodes. You'll have some quantum information, usually qubits, and it's usually in some kind of pure state, and then you're sending it through a channel. Now, what components you need here are, well, the sender needs to generate a qubit, so you need a qubit source. The sender needs to put some information into the qubit, so you need something to encode information into the qubit. The qubit needs to travel somewhere far away, so you actually need a qubit channel to send it away. And then finally, your receiver needs to read out the qubit, and so you need some kind of detector on the end. I've left out the decoder, which also the receiver would need, but in general, you require probably the same parts, pretty much the same parts as an encoder. So what problems do we run into when we try to operate a quantum network in this way? Well, actually, one of the first problems is loss, which is similar to in a classical network over a long distance. Even though your ideal channel is lossless, but real channels always have some kind of loss, even if it's very small. And then the second problem is kind of unique to quantum network systems, or in a system where you're sending quantum information around, which is that as you send your quantum information through a really long distance, your photon, even though it interacts really weakly to the your qubit, even if it interacts very weakly to the environment, will end up interacting with it, and then eventually instead of a pure state, you'll have a mixed state, which I've denoted over here with the summation. And this coefficient right out front is actually a classical probability, and there's no definite phase between the kind of classical probability of like quantum states that you can measure. If you've ever seen a density matrix, that's exactly what it is. So those are the two problems that we have in a quantum network. So now I'm going to try to argue that photons are one of the best carriers of quantum information for long-haul transmission in a quantum network. And the reason for that is because, Well, we have really mature fiber optic telecommunications infrastructure. It's what your Wi-Fi runs on these days. That allows near-infrared lights to be transmitted with extremely low loss. So let's put some numbers to it. When we talk about near-infrared light, we're talking about a wavelength in vacuum of 1.2 to 1.6 microns. So if you ever hear anyone talking about telecommunications band or telecom band in the context of optical communications, this is the wavelength band that they're referring to. And also extremely low loss. This is kind of a maybe a high number, but it's 0.3 dB per kilometer. That basically means that you're losing 3 dB per 10 kilometers, which means you're losing half of your light's power every 10 kilometers, which actually is pretty good, although 10 kilometers doesn't really get you very far, depending on where you are. So that takes care of the problem of loss. What about the problem of decoherence? Well, it turns out that interactions between individual photons and also between a photon and a transparent material is extremely, extremely weak. And so that actually takes care of your decoherence at kind of moderate wavelengths, moderate propagation distances. Now then, like I said, with loss, you're still losing half of your light over, like, let's say, like a pretty small number of kilometers. So actually, even after all of this, we probably need a repeater. And in our case, we need a quantum repeater, which you've probably heard a lot about in the last few talks. So the slides are repeating a little bit in the last few talks. So actually, I'll just refer you to the other short courses in the winter school. Suffice to say, the only thing that's different here is that you start needing entanglement as a resource instead of just like pure single qubit states. So now, let's go back to, so assuming that we are using photonic qubits for long haul communications, that means that all the components that we need to prepare, manipulate, transmit, and also read out are implemented as photonic components. And so here is a rough table of like how the components network components we talked about way at the beginning maps on to kind of devices that are already photonic devices that have already been that we work with. And so, for example, the qubit source, we have lasers, which are also used in classical communication systems. And in addition, you have single photon sources. The reasons we have lasers in here is that there are certain encodings of quantum information that can use lasers instead of, but not necessarily qubits. In the encoder, you'll be manipulating the single photon a lot, and you'll be mapping its initial state to a final state. And for that, you actually need a bunch of active components like switches, modulators, polarization rotators. Usually you're trying to do that with an electrical signal. Or if you're doing it really, really fast, we call it you're using an RF or microwave signal. And then next, for the qubit channel, it's usually a waveguide. And between nodes in a quantum network, you're basically working with fiber optics networks, which we're going to assume here for the rest of the talk. If you've been to the talk yesterday about network hardware, you'll know that some free space ground to satellite schemes are also under development, but it's a lot less mature than the optical fiber networks. And then intranode, so you have all of these components, your source, your modulators, whatnot. You need to route them to and from each other. So either you're routing it through some bulk transparent media with some like mirrors thrown in, or you're using waveguides again. And then finally, for detectors, you can have your single photon, you need to have some single photon detectors to do readout of qubit states. And then you probably need some standard photodetectors to work with your classical channel that you'll often need in a quantum communication protocol. And finally, for a quantum repeater, what you're usually doing is entanglement swapping, which you might remember from some of the talks previously, which involves doing Bell state measurements. And actually, it turns out that you probably most of the previous preceding components, especially stuff like beam splitters, ideally tunable, and you will need entanglement as a resource. We won't be going too much into that for the purposes of this talk. And now, so we have all of these components, and actually a lot of them need to be implemented at various nodes in a quantum network. You can think of nodes as end user nodes, or you can think of nodes as like little hubs and like metro hubs and that kind of things. But it would be really nice if, you know, the hardware needed for each node was relatively small and relatively cheap, so that we can actually implement a quantum network over a wide range of locales and distribute it to as many people as possible, have as much network coverage as possible. So for that, we actually take some inspiration from integrated electronic circuits, where, you know, initially one of the first few transistor-based computers were enormous, as things are, and now you can fit things into a wafer that you can hold in your hands. Well, now, what if we use photonic integrated circuits to reduce the footprint costs and maybe also energy consumption of components at quantum network nodes? This is something that can help accelerate kind of usage of a secure quantum communication over a long distance. However, so as is probably fairly common knowledge, integrated electronic circuits are mostly made out of silicon, and silicon is kind of the material bar none for electronic integrated circuits for various reasons. But it turns out that for photonic integrated circuits, there's a whole zoo of materials that people have been trying and have tried and are trying to make photonic integrated circuits out of. And one of the first things people do is that, okay, if we have already a bunch of stuff that is in a sense standard semiconductor process, like various silicon-based compounds and also 3.5 that was explored for more other semiconductor purposes, you can make that into photonic, make that into a material platform, and then you have some other stuff like diamond, which is in bulk, but you know, you try to make some devices on it and see how far you can get. And then things like aluminum nitride or lithium niobate, which previously was mostly used in bulk, but then in recent years, you know, or past decade, I guess, you can start making in wafers. So for this part, I would like you to spend a little bit of time to fill in this blank in a Zoom poll, which I will launch shortly, like right now. Wait, I see there's a little bit of a typo here. Sorry about that. In lithium niobate, not niobate. Turns out niobate is a different material.
That's a good point. On my screen, Paul stopped the silicon carbide. I got a little worried, but there's maybe people hold out.
Yeah. Okay, so we have the results. So it looks like it's pretty close between well, first we have InGas. People really like InGas, and then we have silicon, and then we have lithium niobate and silicon nitride. diamond has a shocking number of votes. So this is kind of an open-ended question that would be good to keep in mind as we go through the various components and give you examples of what components exist and various things over the course of the next 2.5 hours, I suppose. Yeah. So now that was the end of the introduction, and for the next part, I'll turn it over to Marko for a quick blast through passive and photonic circuit elements, passive and active photonic circuit elements that are generally classical in nature, but as Marko alluded to previously in the talk, for a quantum network, you need all of these elements to function with incredibly high performance. So I think Marko is sharing the screen now.
Perfect. You guys can see my screen, or CJ, can you see my screen?
Yes, sir.
All right, and also there's CJ. Maybe you can take over Q&A. There's a lot of questions. I encourage everybody to be active there. That's a good way to communicate. Given that we are about 40 minutes in and that we covered only introduction, I think we'll do one of the two, go faster or skip slides. So we'll probably do both. So I would like to now to maybe talk a little bit about a subset of passive and then extend this to active components that are needed for classical and quantum applications. And I maybe before I go into this, what I want to say, the reason why I personally am super excited about quantum photonics, in particular quantum application photonics, is because this kind of really challenge of making the smallest loss, the fastest, the most efficient, most integrated kind of devices that you can, which will then definitely find applications in classical field as well. And so this kind of synergy between quantum and classical is quite nice. Integrated photonics is relatively simple. There is a handful of kind of components, library or alphabet, if you will, of components that you need to make essentially anything. These are passive components. Is shown here. In addition to these, if you add a little bit of gain, and we'll talk a little bit about this later, or absorption, but particular type of absorption, you can make detectors, lasers and detectors respectively, and that's pretty much everything you need. So I will spend a lot of time talking about waveguides. As I mentioned, we'll do take somewhat pedagogical approach, and hopefully it's of interest to many of you. And then we'll show some examples, kind of without going into details how these devices are fabricated. Basically, we talk first about waveguides, and then we'll put two waveguides together to make various types of couplers. These four devices here are splitters, directional couplers, like here, multimode coupler, interference-based couplers. We will not talk a whole lot about resonators. I'll show maybe some pictures of resonators, but resonator is nothing but a bent waveguide in one of its forms. We will talk a lot about interferometers because they're really, really important for quantum photonics, and both passive and active version of it. We will talk a little bit about gratings as a way to bring light on chip, but we are not going to go into details of it. And extended version of grating is a field of photonic crystals that's very dear to my heart and very actively researched in the photonics community, but unfortunately we won't have a lot of time to talk about it. Maybe show a few slides. So we'll mainly talk about waveguides basically, and that's kind of what we'll end up doing. And so that basically summarizes in words the picture that I showed on the previous slide. And so before maybe we talk about waveguides, we need to first, so here we're going to start all the treatment that I'm going to be sharing with you is going to be classical, and light is going to be considered to be a wave. And then only when we start looking into light matter interaction, when we talk about active components, we may need to quantize light, but we will not do this. We will not quantize light here. We'll just introduce you to this differently. So basically, if I have electromagnetic wave propagated in free space, one of the shapes that the electromagnetic wave can take is a plane wave. And basically what this means, it's illustrated on this figure to the right. Basically, electromagnetic wave has electric field and magnetic field component that basically orthogonal, and they are also orthogonal to the so-called vector k, which is the propagation direction of this electromagnetic wave. This is so-called transverse electromagnetic wave that propagates in free space. Unfortunately, this solution is only valid in free space, and as soon as you start bringing light on chip, or even if you just put a block of material in front of this electromagnetic wave, this wave is going to scatter or reflect, or both, depending on the size of the object you put in its path. And this simple treatment doesn't hold anymore. But what we can do in some cases, we can actually study propagation of wave piece by piece, kind of piecewise ways, look how wave propagates in one medium and then the other medium, and then match boundary conditions. And that's how actually you can get a lot of intuition about light propagating in optical waveguides, for example. So this is now right now free space. The electric field of this electromagnetic wave can be basically can be shown starting from Maxwell's equation, can be derived and be shown that it has following form. So it's basically, it has some polarization vector. In this case, we're talking about linear polarization, but this polarization can be circular or elliptical. Generally speaking, we're not going to talk about this in great detail. And then has some harmonic dependence on time and space. Basically, this wave is periodic both in time and space. Omega is frequency, as is shown here. It's basically 2 pi times frequency of this electromagnetic wave. And frequency is related to wavelength as c over lambda, basically c is speed of light. So as shown here. And more often than not, we actually write these things in a complex form, phasor form, where we use Euler formula. And so basically, we would take real part of this product here, which is A times e to the j omega t. But I just want to point out that j in engineering is used to denote square root of -1, whereas in math, maybe you have seen square root of -1 is being labeled as I. Because I'm an engineer, I'm going to use J. And so this is the way of propagating free space, and something that we'll talk, that we in photonics talk a lot about as intuitive way to understand how light propagates, are so-called dispersion diagrams. And dispersion diagram is basically shows dependence of the frequency of light to its wave vector. Okay, basically frequency is tells you how many oscillations per second you have in your wave, and wave vector k, amplitude of it, tells you how many oscillations in space you have, tells you something about wavelength. So k is 2 pi over lambda, and lambda is wavelength. It's all shown here, and omega is 2 pi over t, where t is period in time. And for simple free space propagation, this kind of dispersion relationship is relatively straightforward. It's a straight line because frequency of light is proportional to the speed of light, basically. So nothing unusual here. So now what happens when a wave is incident on a boundary, maybe you've seen this when you're swimming in a swimming pool. If you look at an angle to the surface between water and air, basically light, you may see the bottom of the pool. Essentially, light can bounce on the interface between water and air, as shown in this little example. And this is the concept, basically the phenomenon of total antenna reflection, where basically light incident at the interface and light traveling in a medium with a high refractive index, medium that slows light down more, basically due to this kind of bending Snell's law, that due to the Snell's law that it kind of describes how light bends at this interface, you can be in a situation that all of the light incident in the interface is reflected. So basically, if light is incident vertically to this interface, as shown here, some of the light gets reflected, some light goes through. But as this angle of incidence increases, eventually all of the light gets reflected. And this happens when this angle of incidence is a critical angle. And so in order to kind of see just a little more closely what happens here, we are here considering so-called T polarized light, where electric field vector is along x-axis. X-axis is illustrated here, is perpendicular to your screen. And in that case, basically this equation that I showed you before for electromagnetic waves, it can be written like this. And because this electromagnetic field in medium N1 is still transverse wave, it will have propagation. A wave vector will be only in the direction of y and z. There's no wave vector in the direction of x, in the direction of electric field, because it's transverse wave. And so all I showed here is this wave vector k can be broken down into propagation along y-axis, which is perpendicular to the interface, and propagation along z-axis, which is parallel to the interface. And so this is nothing but just rewriting this equation here. And here I'm defining all of these figures of merits that I'm using. So I'm not going to read them out, but you have it for reference. And so what happens when light is incident, this is numerical modeling of this situation. When light is incident, basically light comes from here and gets reflected. And so for a few things you can observe that this kind of simple picture of ray, we call so-called ray picture, that we consider is not accurate. Actually, light does not, it appears that light, the beam that hits here, doesn't quite reflect at this point. It reflects a little further away. And this is so-called Huysken shift, essentially, that is due to the fact that light, this boundary is not very hard. Light kind of feels a little bit what's on the other side. And because of this, there's this shift. And another thing is you can see in this region here, there is some interference. And this interference actually, you will see on the next slide, forms standing wave pattern in the direction of y, in the vertical direction. And this standing wave pattern is going to be crucial to form waveguide modes. So if you look a little closer into this thing, so here on the left, what I'm showing is what happens when basically in this situation, light incidence and interface and gets reflected. And then I interfere, forward propagating and reflected light. What's going to happen? Light is basically going to form the standing wave pattern, and this whole standing wave pattern is going to propagate in the direction of z. Okay, so this is the, like mathematically, you can show this is the case, and intuitively, hopefully, is clear from this simulation here that shows how this standing wave pattern emerges in this region. Okay, and so basically, what happens as light is incident and interface, it gets 100% reflected. Standing wave pattern is formed here. Light does feel what's on the other side. There's so-called evanescent tail. These evanescent fields are really important, as you will see. You can use them to make very interesting devices. So you know, if I put an object here, for example, molecule, that molecule will feel some electric field, but if molecule is far away, it's not going to sense any electric field because this light doesn't propagate. It's just exponentially decays. Okay, and so if I did the math basically correctly, then you would show that in this blue region, in region 1, total electric field of incident light and reflected light can be written like this. So standing wave pattern is formed. You see that now in cosine, there is no basically, why is the standing wave pattern? Because there's no time dependence anymore, right? So there's, you used to have cosine omega t minus ky, but now there's only ky component with some phase shift that I was describing. And so then how can I make waveguide out of it? Well, basically, if I now consider this optical standing wave and I start in precisely in precise positions, I introduce an additional interface. For example, if I put another interface N2, N1 here, or here, or here, and these locations are chosen so that basically if I put this interface, evanescent field would just extend and wouldn't further perturb the standing wave profile. I can basically, if I put these interfaces, I'm essentially not going to perturb this standing wave profile significantly, but I'm going to form waveguide modes. So this is illustrated here. So if I bring another interface at different thicknesses, at different locations in standing wave pattern, I can trap light like this. Light can have one oscillation, or I can have two oscillations, I can have three oscillations in space. And still in interface in material N2, the light is going to evanescently decay. So basically this light, this optical mode, let's actually take a look at the fundamental mode. This optical mode now is trapped in vertical direction and propagates in Z direction. And this is essentially a mode of an optical waveguide. This is so-called slab waveguide mode. I'm not going to go through math here. This is just for your reference, how you can figure out so-called dispersion, which is relationship between wavelength and frequency, the relationship between frequency and propagation constant along the direction of propagation, which is E in our case, can be determined by this equation, which can be derived from stuff that I showed in the previous slide. So what you can see now that in free space, actually these modes were straight lines, okay, in a medium with higher refractive index, which was medium 1, this light propagating had this kind of dispersion relation. A light propagating medium 2 had this dispersion relation, but when you put two together, actually these dispersion modes bend, okay? And what's interesting is that turns out the derivative of these curves is something called group velocity, that basically it's very important figure of merit when designing optical waveguides. If you need to, if the dispersion itself and group velocity dispersion is particularly important. So that is something FYI. We're not going to talk a whole lot about this here. So basically, bottom line is, if I pick particular frequency, okay, let's say I pick frequency here at this point, then if I want to know how many waveguide modes does my waveguide support, I just basically draw a line to the right, and I would see that they have 3 intersections. They're not easily seen here. 3 intersections, and these would be these first 3 modes, fundamental, first mode, and second mode of my optical waveguide, okay? And also there are conditions when there's only one mode, and this is so-called single mode operation. So if frequency of light is chosen to be below this point here, then only one mode be supported, which is this fundamental mode as shown here. So bottom line is, by choosing the thickness of this waveguide, typically this thickness is on the order of wavelength of light. By choosing refractive index of both what we call here core, which is the where light propagates, and cladding, which is region where light is evanescent. By choosing these refractive indices, by choosing thickness of the waveguide, and by choosing properly frequency of light, I can have light propagated in single or multi modes. And for many applications, especially in quantum, actually single mode operation is desired. And because this goes around this problem with dispersion, because these different modes, as I mentioned, the velocity with which they would propagate, the so-called group velocity, would be derivative of these curves. And if you can see that each of these modes has slightly different derivative for given frequency, which means they all propagate with different speed, which means if I excite all of them, then they will just separate in time, and that's not very good. So normally we want to work with single mode, and only consider that mode as single photons or a laser field propagate inside the optical waveguide. And so these are some of these considerations that I mentioned already. It's really, when you design a waveguide, it's important to consider how many modes do you need. Is it single mode? Is it multi-mode? Do you want thicker waveguide or thinner waveguide? Do you want big index contrast between two core and cladding materials? Do you want this light to support different polarizations of light? So far, we were talking only about so-called T-polarized light, but there's other polarizations you may consider. Do you want more or less dispersion? So that you can, fortunately, you can actually, depending what your figure of merit is, you can design for all of these, right? So these are 2 different polarizations. And I just want to point out, connect to something you've seen before in one of the previous lectures. You also learn about optical fibers and optical fiber modes. And optical fiber is basically a special case of these slab waveguides that I discussed here, right? So basically, optical fiber is nothing but this kind of interface between 2 materials, but not in cylindrical coordinate system. Okay, so for example, if you want to send a lot of light in a waveguide, very high intensity, you may want to have big waveguide. Otherwise, you may start experiencing nonlinear effects. If you do want to experience nonlinear effects, then you don't have to worry about this. On the other hand, if you have waveguide is very thick, it becomes multi-mode, and that can have issue for pulse propagation, for example. So it really depends on application, what you want to do. And this simple equation that we didn't derive, and maybe I don't expect you to immediately see all the subtleties of it, but basically can be used to figure it out and to design your waveguide. Another thing that I just want to briefly mention, because it's actually a big challenge in integrated photonics, is how do you bring light in and out of these waveguides, right? So as I mentioned, these waveguides typically are roughly turns out to be roughly the thickness of the thickness of the waveguide is on the order of wavelength, half wavelength in a material. So for example, lambda divided by 2 and 1 would be good assumption for the thickness of this waveguide. So if lambda is 1 micron and this is made out of glass, which is 1.5 refractive index, then thickness is on the order of 300 nanometers. So light is really, really squeezed tightly. On the other hand, if I want to bring light in, if light comes from the laser directly, that laser spot is maybe, maybe a few millimeters across. If it comes from the fiber, if you remember, the mode is on the order of 10 microns. So it becomes extremely difficult actually to bring light from fiber or from laser directly into the waveguide. So that's why often we use lenses, or sometimes we use the lensed fiber or other ways, as you will see, to bring lights in. And I'm not going to go into great details, but if let's say you use a lens, then the question is, which lens are you going to use? Do you want a really lens that's going to tightly focus the light so that this angle alpha is really large, or you want a lens that's not going to tightly focus the light, and that makes alpha is very small. Lens, there's something, if you're familiar, numerical aperture of a lens is the important figure of merit that is basically proportional to the refractive index of the material where lens sits. This is this N out, and times sine of this angle, right? So if you have very high numerical aperture lens, you'll be able to focus light very, very tightly, roughly lambda divided by NA on the order or thereabouts. But so spot can be very small. The problem is if spot is very, very small, then you will have rays that are maybe hitting this interface between two materials in a way that doesn't satisfy a critical condition and doesn't satisfy total internal reflection. So light is not captured actually by the waveguide. So that's a huge problem. Alternatively, if NA is not very large, if NA is small, if alpha is small, then turns out your spot is giant. So yes, all of your light can go in, but spot is huge. So simply by overlap, if you consider spot of millimeter and waveguide cross-section of, let's say, half micron by half micron, no light goes in. So you really need to carefully choose the numerical aperture of the lens, roughly to be smaller than the numerical aperture of the waveguide, which actually incidentally it's not too difficult because numerical aperture of typical waveguide that we will consider is very large, and numerical aperture of the waveguide can be written like this. So for kind of examples that we will often consider a refractive index of a core, let's say silicon is 3.5, cladding, if it's glass, is 1.5. So this kind of is square root of 10, and normally numerical apertures of the good lenses are less than 1, and if you put them in kind of medium, like in some sort of fluid, they're maybe just above 1, right, between 1 and 2. So this condition, like it turns out, basically you want to have as high numerical aperture lens as you can, while making sure that this condition is satisfied. Okay, so that's one of the ways, and typically, as I said, we use lensed fibers to do this, which is very, very convenient way of doing it. Other ways, in addition to this kind of lens coupling or tapered fiber coupling that you can use to bring light in, is so-called butt coupling technique, where it's particularly good if you want to bring light directly from the laser or some other waveguide that has similar mode diameter, similar cross-section to the waveguide you're considering. So, for example, if laser diameter is maybe micron across or something like that. So that actually can couple very nicely to the waveguide properly designed, even without any lens in between. Okay, this also can be fiber, but for fiber, as I said, we need to consider this. We probably need to have something that's called spot size converter that we are not going to talk a whole lot about here, which is on the end of the waveguide. You can actually shape this waveguide a little bit to extend the optical beam so it very nicely couples to the fiber. So these are probably the most common approaches. Prism coupler is kind of convenient for slab waveguides, not very often used in integrated photonics, I would say. And by the way, you may want to consider, okay, what's the big deal? Why don't I just shoot light from some angle and light is just going to get in? the issue is if the waveguide is symmetric, just how light can get in. That means if light can get in, that means total internal reflection here is not satisfied, which means it's not going to be satisfied on the other end either, and therefore light is going to go down, right? So that's not going to work. That's why often you need this kind of prism coupling or adiabatic coupling that's not indicated here, but I'm going to show on a later slide. And most common, one of the most common approaches, not the most efficient, but it's really, really versatile approach, is grading coupler, where basically what you do, you come with the light from out of plane, and basically this grading coupler kind of assists, breaks, kind of, if you will, total internal reflection condition here, kind of changes the momentum of incident wave, changes the K of incident wave that allows you to couple to the modes of the waveguide, right? So, and these modes of the waveguide, once creating ends, actually this mode, this kind of eigenmode of the structure just propagates. So this is very efficient way of doing, well, very versatile, very simple way of doing this, but not necessarily super efficient. Though they are designs, but not very efficient. Maybe, you know, maybe 10-20% without doing something magical. But if you put a lot of effort into it, use multi-layer gradings, you can go to, you know, above 50%. And this is this kind of evanescent coupling. So here we bring two waveguides, and we will see the structure again in the context of directional coupler. We bring these two waveguides together. Okay, and so if I have one waveguide in isolation, mode just propagates happily. But if I bring another waveguide nearby, actually now two waveguides can feel each other, and light can jump from one waveguide to another waveguide. And this is actually a very convenient way to bring light from first waveguide to the second waveguide. But then the question is, you know, how did you bring the light in the first waveguide? Well, maybe the first these waveguides may not have to be the same. Maybe first waveguide is optical fiber that is kind of really tapered and made very, very thin. And this tapered fiber touches your waveguide of interest. And so light can just kind of tunnel from the fiber into your waveguide of interest. So this is actually a very often used technique that can have extremely high coupling efficiency, you know, routinely above 90%, for example. Requires precise alignment, whereas grading is less efficient but doesn't require precise alignment. And so all of these things that I discussed so far and all the waveguides that I discussed are so-called slabbed waveguides. So they're actually not very practical because they only confine light in one direction, right? In this kind of Y direction here. In Z direction, okay, we don't want to confine light. In Z direction, light propagates, but in X direction, actually light also can propagate. So it's not localized. So this would be like slab mode, light just like covered whole surface of your wafer. So this is not very useful because we want to integrate many components on the same chip. And so in order to do this, we are typically using sort of waveguides that give you additional degrees of confinement. And these are so-called, we rely on 2D light confinement. And the easiest way, for example, as shown here, or maybe as shown here, it's kind of, we refer to this here as immersed strip. It's a waveguide which has a high refractive index cladding that sets high refractive index score that's completely immersed in a cladding, that lower refractive index. And so now you have total internal reflection on two interfaces, on top and bottom interface and left and right interface. And this total internal reflection interface basically confines the mode now in basically X and Y in cross-sectional plane, and light propagates in Z direction. Unfortunately, math of this is actually quite involved, and almost never we actually there are a few exceptions, but in so-called low index contrast waveguides, but almost never we actually use this use analytic solution to study these waveguides. We often resort in integrated photonics to tools like finite elements modeling or finite difference time domain modeling. CJ, I noticed there's some chat questions, Q&A. Is there anything for me that I should feel free to interrupt me if there's something?
Yeah, I'm working on answering them. Sorry, I sent one to you by accident.
No problem. If I just can't monitor at the moment. Okay, so this is one, and more often than not, waveguides that you will see in literature are so-called ridge waveguides. So basically, you have some material, let's say silicon on silicon dioxide that you buy, and then using process of microfabrication, you remove a little bit of silicon, and you make this ridge. And so now light has cladding at the bottom, which is glass, silicon dioxide. On top, cladding is air. Still, both of these refractive indices are smaller than silicon, and therefore light can propagate in silicon waveguide. Ribbed waveguide is another popular geometry, just like the only difference is you don't etch this kind of, we call this device layer, where devices are made, in this case, for example, silicon. And here is an example, for example, a ribbed waveguide made in silicon an insulator. This is silicon on insulator, silicon dioxide. Here is a ridge waveguide in indium gallium arsenide phosphide, and so on and so forth. Okay. Are there any questions that I should answer at this point? All right, maybe I'll move along. So this all assumes now lossless propagation, right? So we used Maxwell's equation, we discovered the modes of the slab waveguide, and then we just extended this without any math or modeling. I just told you, okay, this works in other dimension, and that's how we can have confinement in 2 dimensions, and then light just propagates in a 3rd dimension, and that actually works really well. In fiber, this is given because of cylindrical symmetry, but also works in these other geometries. So, you know, but what if actually if my fabrication process to make the silicon waveguide is not perfect, if I have some roughness, maybe, you know, people can think about this and put in the Q&A, what would happen if I have some bumps, for example, of what if I choose material that has some defects that absorb light or emit light, what can happen? So basically then we need to modify our treatment, and fortunately in most cases it's sufficient. We can do this phenomenologically or using perturbation theory. If losses or gain that light that propagates in a waveguide is not too great, we can actually do this perturbatively, and so or phenomenologically. I'm going to show a phenomenological approach. So basically, if you remember, our optical mode in free space here, this is not waveguide mode, but in free space, propagation of plane wave can be written like this. We said that k vector, this wave vector, is 2 pi over lambda times n. So what happens if I have some sort of loss? Well, if I have some sort of loss, it turns out that refractive index, it's not real anymore, actually. Refractive index becomes imaginary, and so here I'm explicitly writing this, that refractive index becomes imaginary, and so then this exponential equation separates in 2. So I still have this kind of complex phase factor, so this is light that propagates, this is still like traveling wave, okay, but it will have this additional, and this is all real here, it's additional component that will actually, in the case of loss, which means that imaginary part of refractive index, it needs to be negative. In the case of loss, this is going to become attenuation. In case of gain, if I put some gain material here, this is positive, and if electric field intensity is going to grow, and so this is going to be exponential growth, right? More often than not, we deal with loss in almost every system, except if we are explicitly building laser or an amplifier. So basically, I'm going to rewrite this and introduce this kind of absorption coefficient alpha as defined like this, and therefore electric field now can be written as, it has 2 parts. One is parts that propagates, and the other part is attenuates, right? So this is, you can think of it, instead of sine and cosine, now we have exponential decay, and underneath provides the envelope for electric field, and underneath light will basically just oscillate. Okay, and so where you can see that this actually indeed the losses, where they can come from, and why is it that this complex treatment actually makes sense. You can see basically, if you look at Maxwell's equation, this is one of Maxwell's equations, curl of H equals current in a system plus this is derivative J omega times this D field, right? So J is basically conductivity sigma times electric field, whereas vector D is basically can be written as like a medium permittivity times electric field plus polarization. This polarization basically tells you how does medium respond to electric field. Like in the simplest case, I have electron, cloud, and atom, and if I apply electric field, electron cloud will be displaced a little bit. So this is the polarization. But if this displacement is large, this now is not harmonic anymore, and I have kind of some anharmonicity, which gives rise to nonlinear components. In most cases, except for what CJ is going to talk about, if I ever shut up, is we'll just deal with linear part here, okay? So if I rewrite this equation, you see that now this kind of sigma introduces, this conductivity of medium introduces some imaginary part in epsilon, and because epsilon is square root of, refractive index is square root of epsilon, and now epsilon has real part and imaginary part, you can expect that the refractive index will also have real part and imaginary part. Okay, so essentially conductivity is one way how you can introduce losses, and this conductivity comes from basically free carriers. So if I have in my medium some free carriers, if medium is doped, like the silicon has some background doping, I'm going to have a bunch of free carriers, and these free carriers will be absorbing. They will really give some conductivity, and there's going to be absorption. This conductivity ideally is not large, but you will see there are actually the situations where you really want to have a lot of carriers. And unfortunately, the penalty you pay is you have a lot of loss in silicon. And so for some applications, silicon is not actually a very good material. In addition to these free carriers, absorption can come not only from sigma, but absorption can come from chi, because chi actually is not only necessarily a real number. What chi describes, as I mentioned, is how does atom, and here's I'm showing an atom sequence, atoms in a crystal, how does electron cloud of an atom respond to electric field due to optical field, basically. And in simplest case, this is harmonic oscillation. It's like you have some electric Coulomb force that acts on electron cloud, and it's going to drive this electron cloud up and down. But there is also this process actually has some loss, which is captured phenomenologically by this kind of first derivative of displacement of electron cloud. And this is by the way, so-called Lorentz model. And when you do math on this thing, you find out that actually this susceptibility of material is not real, but it has this kind of Lorentzian shape. And that it does have actually imaginary component as well. So these bound electrons, as they respond to electric field, they also can introduce loss, okay? And by the way, this kind of simple model, Lorentzian model, is actually extremely powerful because it can be used to model response of any material ideally far away from the band gap, right? So here's I'm showing instead of having like one oscillator, so this is kind of one oscillator model where material has a response as a one oscillator. Material may have different dynamics that can be captured with different kind of different oscillators, and this is like captured with 3 peaks, for example, in absorption coefficient, right? And more generally speaking, refractive index square or epsilon relative can be written as a sum of these various Lorentzians that give rise to dispersion and also absorption if you hit these peaks, right? So here's for example, so-called Selmer equation, which is a very powerful way to actually model materials numerically. Like when we want to see how light of different wavelengths propagate in medium, we need to kind of understand what is refractive index of these materials. So we use these equations day in, day out in our lab. Though lately, often what we do, because there's discrepancies between these theoretical materials and measured materials, we actually go and measure our own, do our own measurements to kind of get better agreement between theory and experiment. Okay, and here I'm just showing you for your reference how, in this case, dispersion, or how this kind of Lorentz model and this response of electric cloud to electron cloud to electric field, how actually results not only in absorption, that's not shown here, but results in dispersion, which is refractive index being dependent on wavelength. And this is really important, as CJ is going to talk about. Is actually when you talk about nonlinear processes and whatnot, it's actually this kind of wavelength dependence of refractive index. It can be a huge problem, or assets, depending what you're trying to do. And it is actually a consequence of how material responds, how these electron clouds responds to electric field of light. Okay, so when you talk about losses, the main kind of loss mechanism in an optical waveguide are then free carriers. Bound carriers, not so much. We typically operate away from these resonances unless we go to short wavelengths, like visible or UV wavelengths. Then actually these bound carriers become a problem. Also, we try to stay away from band gap, right, of the material. If I'm trying to make lossless waveguide, I want to operate this. I want to make waveguide out of the material that's not going to absorb light. So I need to operate away from the band gap. In the case of silicon, typically we operate 1.5 micron. If I want to make a device that operates in visible wavelength, I cannot use silicon because silicon is going to absorb. So I may want to use diamond or lithium niobate or something like that. And scattering is actually another thing. So presumably, when you design a waveguide, you kind of thought about bound carriers and band gap. So you chose right material. Free carriers, as I said, depending on application, you may need, so you won't need to worry about this. And then the other thing is you need to worry about when you make a waveguide, do I have scattering? And scattering comes from the fact that your fabrication is not perfect. These sidewalls that I showed you in this cartoon that look like beautiful straight sidewalls, they are occasionally neither straight, not perfectly smooth. So any bump on this sidewall is going to break total internal reflection condition, and it's going to result of light leak out of your waveguide, and that's a loss. And this is actually one of the biggest loss mechanisms in waveguides. And then, you know, one thing that I realized I didn't capture here, sometimes you have also defects in the materials. You know, when you make cladding, for example, of silicon dioxide, you treat it as a perfect silicon dioxide, perfect glass, but in reality, when you deposit this material in a clean room, it may have all kind of junk in it. It can have, maybe it's not really SiO2, maybe it's SiOX, or maybe it has a little more silicon, a little less silicon. And all of these defects and impurities can introduce additional losses. So that's another thing you need to control. So this would be absorption, fabrication-induced absorption. It's extrinsic, right? It's kind of not, shouldn't be there, but it's there. And then, of course, if you bend your waveguide, like shown here, if you make some sort of sharp bend or resonator, which we're not going to talk a whole lot about, then actually light, also total internal reflection condition, is broken. If bend is very, very sharp, basically in the ray picture, the interface, the curvature interface, if it's larger than, let's say, wavelength or something like that, actually, actually a lot more than that, then light can leak, right? And it's typically, you know, basically what happens, modes get pushed closer to the interface and total internal reflection condition is broken and light leaks. In addition to these, you can also have nonlinear losses, but you know, they are typically happen at high powers, and this is not very common in quantum photonics. Okay, so now this is the waveguides. This is basically the simple waveguide is used to bring light from point A to point B. Often you want to split light. You want to send light not only from A to B, but want to take signal from A and send it to B and C. For that, we use, in the free space optics, we use splitters. Splitters is actually, this kind of classical splitter is a relatively simple device. It relies on total internal reflection. So essentially, its typical splitter is prism that consists of two triangular prisms, or it's cube that consists of two triangular prisms. If I have only one triangular prism, basically, then if light incident is going to meet this interface in total internal reflection condition, it's going to be entirely reflected. So there's no splitting. This is just like mirror, basically. But if I bring one more interface, but now bring it close to this first, I would take one more prism and bring it close to this first prism, and this spacing is such that actually field from first prism, evanescent field can actually feel the second prism. This evanescent field, once it feels the second prism, is going to become guided, and it's going to travel again. And this is so-called attenuated total internal reflection or frustrated total internal reflection. But basically, by controlling this gap, light, some fraction of light can make through this gap, and some gets reflected. And by controlling this gap, you control, is the splitting ratio 50-50, 10-90, or whatever you need it, right? So this is how you make the splitter in a free space. On chip, we use pretty much a similar idea. We use evanescent waves. So this is we're going back to slab waveguides. We have two slab waveguides. Okay, one is let's assume what I want to do. I want to, in this case, I'm actually building directional coupler. Okay, so which is related to kind of this beam splitter, but it's the device that would bring light from one waveguide to the second waveguide, right? So this would be extreme case of all of this light, instead of going up, going this way, right? And then if I control this separation here, or in the case of the directional coupler, if I control this length of two waveguides interacting, then I can control, do I get 50-50 splitting or 0-100 splitting, or so on and so forth. So how you can think about this intuitively is following. If I have a single waveguide and I have single mode, so this is like cross-sectional profile of electric field of this single mode waveguide. So now this mode is eigenmode of this single waveguide structure. However, this mode is not eigenmode, it's not solution to two coupled waveguides. From quantum mechanics, you may remember, if you have two coupled quantum wells, you have even and odd combination that are eigenmodes of the system. The same turns out to be in the case in photonics. If I bring two waveguides together, they will couple, and this coupling will give even or an odd combination. And so now as you remember, maybe these two modes, if you remember from when we talk about dispersion, actually will propagate with different velocities. They will have different phase velocities, these two different modes, okay? They don't propagate with the same speed. And so then what happens, this first mode, I can, in kind of to zeroth order, I can represent as geometric, as basically as a sum of these two modes, because this peak and this peak will add, and this peak and this negative here will subtract. So kind of the first order approximation, if I add these two guys, I get the mode of the single waveguide. So this is what I have at the input. It's even sum, right? And then as these two modes propagate, they propagate with different phase velocities, which they have different effective indices. They have different beta factors, okay? So we took omega out of equation. Because of this beta of even mode and beta on odd mode are different, after some period of time, there's difference basically. I can take common factor out, and there's difference in beta that remains inside. And if I choose the length of my waveguide coupler appropriately, this thing here then becomes pi, which means that this odd sign in front of odd becomes negative, which means instead of even plus odd mode at the input that I had, now I have even minus odd mode at the output. And if I subtract these two waveguides, basically you see that I end up with something that looks like all the light is in the second waveguide. So this is very simple, intuitive way how you can think about these things. It's actually related a little bit to perturbation theory in quantum mechanics. And if you do math, you see that actually light can, by controlling the distance of these two couplers, light can be completely coupled to one waveguide or the other waveguide. Okay, and so this is shown here. I'm just going to say, without going into any details, that this is strictly speaking, it can be modeled very nicely using so-called coupled mode theory. And I'm just going to leave this slide here in the interest of time, but you can actually derive all of these things from kind of first principles. And you can indeed see that this simple kind of intuitive picture actually holds quite nicely, but this allows you to actually exactly evaluate what is this kind of propagation constant for first mode, what is propagation constant for the second mode, and so on and so forth. So that requires a little bit of math, which we are not going to do. If you believe me that when everything is said and done, amplitude of light in one waveguide versus another waveguide, A1 and A2, is a function of whatever I have at the input times some matrix, okay? Then, and if you believe me that I did my calculation right, you can you find out that in the case of 50-50 beam splitter, if this distance is chosen such that basically is chosen such that at the output of this directional coupler, I can have a situation with half of the light is in top waveguide and half of the light is in the bottom waveguide. Then I can make my so-called directional coupler-based beam splitter, right? Simply by controlling the length of this thing. Before, remember, I had 100% of light here, and then 100% of light ends up here. But now if I cut this basically shorter, roughly twice as short, then what I'm going to end up having is 50% of light here and 50% of light here. When I say 50%, I really mean intensity. When you look in the amplitude, when you do the math, you realize actually that there are some actual factors, phase factors, that are really important in this case, because we are making interferometer eventually. So these actually, these are really, really important to keep into account because they keep track of the phase of light, okay? And the same is true for actually classical beam splitter. We didn't just beat this to that. And so now with this in mind, what I can do, I can actually make even more complex device. So what I can do, I start with this 50-50 directional coupler, 50-50 beam splitter, okay? So I'm writing here what is field intensity, B1 and B2, and the output of this as a function of input, A1 and A2. And now what I can do, I can add a propagation section, okay? And so now when I express field in C1 and C2 as a function of B1 and B2, well, this is just like propagating in this waveguide and propagating this waveguide. These two waveguides are further apart, so the light doesn't interact, so they're not coupled anymore. So all I need is extra phase, okay? So this is this. Basically, the only difference between C and B is there's just extra phase due to propagation. And then I put another directional coupler, which I know how to treat. Now, DA1 and D2 are related to C1 and C2 in following way. okay? And so now if I actually multiply all of these matrices, I can find a relation between D1 and D2. I can find D1 and D2 as a function of A1, right? So basically you can see after a little bit of math that output light in these output waveguides can be described using following way. Okay, so in our case, we assume there is no light at the input A2. There's no light here. All light is A1. It turns out by simply controlling the phase phi, and what is phase phi? Phase phi is phase difference between light propagating this waveguide and this waveguide. So notice, normally I would pick these two waveguides to be the same length, but notice I put some electrodes at the top waveguide. And what I'm going to do with these electrodes, I'm going to actually use them to change refractive index in this arm. And when I change refractive index in this arm, I will slow down light a little bit. And so the light, when it comes here, is going to have different phase than the light that comes at C2. So C1 will have different phase than C2, which is captured by this extra phase factor here. And because of this, actually, this extra phase allows me to control, if you look at this matrix, you can see that if I strategically choose phase phi to be pi, you see that basically you will get basically light will be, this is pi over 2, this is pi over 2. So basically you get kind of like 50-50 here. So if phi is pi, then and if I don't provide any input here, okay, you'll see that most of the light is gonna end up being on top waveguide, basically. Okay, so this is how now this thing is called interferometer. It's called Mark-Zener interferometer, and in addition, actually has this kind of a tunable component that allows you to tune the phase, which allows you to control where light is going to exit. Okay, and so what are some of the maybe I'm going to skip. What are some of the mechanisms that we can use to control the phase of light? Maybe if I could go here. Well, first I can apply heat, because if I apply some heat, I change refractive index, and this changes the phase. I can inject some carriers. If I inject carriers in this material, I will have free carrier dispersion. I will change refractive index, right? Remember, I'll introduce sigma. Sigma will change refractive index. Unfortunately, I'll come along with a loss, but I can definitely use this to tune the phase. I can also use materials, so-called Pockels material, that materials have electro-optic effect, which are materials when you apply electric field, they actually change refractive index itself, right? So there's no carrier injection associated with it. And this is actually the most interesting materials that we will consider. But these Mark-Zener interferometers are extremely powerful. I'm just flashing some examples of components that you can make using Mark-Zener interferometers. So here's, for example, this is, I believe, for Dirk Englund's group. You can make some kind of neural networks, but just by cascading a bunch of Mark-Zeners. You can use you can make matrix multiplication by making a bunch of Mark-Zeners that are cascaded. You can basically build quantum circuits that are nothing but a bunch of Mark-Zeners and beam splitters and some phase tuners. You can, make this at much larger scale. This is for Psi Quantum Company that are trying to commercialize photonic quantum computing, for example. So you can do a lot of interesting things. You simply by using a bunch of Mark-Zeners, bunch of waveguides crossing, a few other components that CJ is going to talk about. These are these photon pair sources and so on and so forth. So with that, basically, we cover like one of these components in great depth. But this is directional coupler as well as the waveguide, and but there are other ways how you can split light that I'm not going to talk about a whole lot, which is multi-mode interferometer-based waveguides, inverse design that are really powerful. Maybe just flash this. Everybody likes to see these pictures. This is from the work of Yana Vučković's group at Stanford. But basically, using inverse design, you can let computer design these coupler sections so that light can be split in weird ways. Like it can be 50-50 split. It can be one wavelength of light goes up, the other wavelength goes down. And these devices are designed by a computer by actually, you let computer decide the refractive index of each of these pixels, essentially. So as opposed to, for example, what I showed you, what human would do, use kind of this perturbative approach to make very nice couplers. So they tend to be more compact and more robust, but also designing is the process is a little different. Going back to ways how you can make modulator, I mentioned briefly that carrier injection is actually often used to control the phase. And this is in particular used in case of silicon photonics, where you have because silicon, which is silicon photonics is one of the widely used integrated photonics platform. As I show you, you can make all kind of interesting components. Unfortunately, silicon photonics, silicon is not electro-optic material, so you have two choices how you can change its refractive index to control the phase. You can heat it up. You can use heaters. That tends to be really, really slow, typically, and you can go as fast as maybe kilohertz or megahertz, which is typically not good enough for many applications. Or you can choose to inject carriers or deplete carriers, because basically you take silicon and turn it into a PIN junction, and then carriers can be injected or depleted, and that changes sigma, which changes refractive index, but also changes absorption, increases absorption. So in the case of silicon, you can make very nice modulator, but they are very lossy. So if you want to make a low loss modulator, silicon is not a good choice. And so for those of you who have silicon as platform for quantum photonics, it is very good for many things, but unfortunately, it cannot go very fast. Certainly, a lot of nice demonstrations have been made, but typically people actually in quantum integrated photonics, people who want to make photonic quantum computers, like let's say PsiQuantum, they use silicon as a platform, but then they don't use this carrier injection, carrier depletion to modulate. Typically, they combine this either with some electro-optic material, like barium titanate is a good one, lithium niobate is something very work one. Dirk Engel is doing a lot of work on aluminum nitride. So use these heterogeneously integrated approaches where you use silicon as a backbone, or more often also silicon nitride, which is even lower loss material platform. But then when you want to make switches, you want to make active device, you bring another material in a picture. And so this is actually a very powerful way of making integrated photonics components. So maybe with that, in interest of time, what I will do, CJ, so what we were going to talk next was actually talk a little bit about lasers, which is, after all, they're used to bring light, to generate light on chip. And maybe I'm just going to give you a quick summary, what a degree is for a laser, and then I'm not going to go into as much detail as I originally planned. But basically, to generate light, to kind of generate these kind of strong optical beams, which are important for quantum as well, and definitely for classical, you typically use these days semiconductor-based light emitting devices like LEDs or semiconductor-based lasers. And so the way they work, essentially, first you kind of excite some carriers, free carriers from valence band. So these are electrons that are basically stuck in making bonds with material. And then you essentially, when you can excite them, give them extra energy, so they become free. They become free carriers. They go essentially get extra energy. So we say they then reside in this kind of conduction band, and when they recombine, they can give back light. And so this is one way to make light emission. Okay, this process of light emission, as I mentioned, when you consider this, you need to consider what kind of material, maybe I'm just going to go here, what kind of material you're using to generate light. Because I said we have semiconductor crystals. Semiconductor crystals have basically, maybe I'll show this kind of Venn diagram in the case of silicon. So this is silicon crystal lattice. This is silicon Venn diagram. These lines are allowed this is dispersion diagram for electron. So these are allowed energies that the electron propagating in this lattice along these directions, these are directions indicated here. So electrons propagating in the lattice. These are allowed energies that the electron can have. Unfortunately, there is fortunately there is a band gap in silicon, which means there's a range of energies where the electron cannot exist. Okay. And this is actually, if you operate in this wavelength range, silicon will not absorb, and silicon can be a very nice semiconductor, very nice photonics material, and this wavelength is in the order of 1.5 microns. However, if you want to emit light, what's going to happen is that silicon has so-called indirect photonic band gap, which means the lowest energy of these kind of free electrons, conduction band electrons, is not centered in K-space, in a wave vector. These electrons don't have the same momentum as these holes, okay? And so therefore, when an electron and hole want to recombine, with this electron wants to go back to kind of valence band to emit photon, actually this process requires some phonons to participate to change the momentum of the electron. This is not a very efficient process. So silicon is not good semiconductor and not good light emitter. 3,5 semiconductors that have so-called direct band gap are excellent emitters because there, the bottom of this valence, conduction band, the top of valence band are aligned. So actually, these electrons and these holes have the same momentum, and therefore they do not require any phonons to participate in the process. And this process is very efficient. And so good light emitter materials are indicated here. The gallium arsenide, indium phosphide, gallium nitride, and so on and so forth. And so all I'm going to say in the end, in the context of laser, when you want to build a laser, what you kind of end up doing is you pick some kind of semiconductor material, typically so-called semiconductor heterostructure, where you're using two different materials with slightly different band gap to put them together. And the reason why you do this is electron can be trapped inside its quantum well. So you have some material that can essentially provide good emission, means this electron and this hole can recombine and generate photon. This photon gets emitted. There's probability of this photon to be emitted in free space, and that photon is lost. That's not very good. But maybe this spontaneously emitted photon, some fraction of the spontaneously emitted photon goes in a cavity, and in the side optical resonator, which cavity is basically a waveguide with some mirrors in the end. Photon hits the mirror, gets reflected. This medium is pumped again, so there's more electrons in an excited state. They get stimulated now to emit, so you get stimulated emission. So now these two photons travel together, hit another mirror, and this process continues. So what you need is this feedback you need low loss, basically. You have low loss waveguide. You need mirrors to provide feedback to turn spontaneous emission into stimulated emission. And you need gain medium that can be pumped, ideally electrically, to build a laser, okay? And so when everything is said and done, this is typical laser curve where you are injecting some current to excite the carriers. You keep injecting current most of the time, nothing happens. And then at some point, you inject enough current, the process of stimulated emission takes over. And then basically laser starts emitting and you get this really nice sharp turn on of the laser light, essentially. So this is kind of like 1 minute summary of how that works. CJ, I think this means you're next. And sorry, I took way longer than I anticipated.
Yep. Time for me. Why don't people take a breather for like 3 minutes while I wrestle with Zoom? Yeah. So we've talked a lot about Marko talked a lot about all of the other components that are relevant to also classical applications that we like to have, and people are trying very hard to implement on integrated photonics platforms. What I'm going to focus on is going to be a sampling of the kind of quantum specific things that we need in an integrated photonic platform. Specifically, if we're trying to use single photons as qubits, we need to actually be able to make single photons. And ideally, we want to be able to click a button and then we always get a photon out. This is what we call a deterministic source. In integrated photonic platforms, we're usually interested in atom-like things in solids, because usually we want to make integrated photonics out of solid things. Those are just easier to work with. And the leading candidates are quantum dots and color centers, which are both kind of, when you break it down, you can kind of treat it like just a level system, like in an atom. And then for some reasons that will hopefully become clear as we go along, we also work a lot with probabilistic sources, where you click a button and then you sometimes get a single photon out. And you might be wondering why we would ever want to use that. It sounds strictly worse. I'll address it later. And those sources typically are based on some kind of optical nonlinearity, parametric conversion of frequency based on some optical nonlinearity. And usually what happens is that you have some really bright pump or pumps going into the material, and it interacts with the material, but it doesn't exchange momentum or energy. And then out comes a pair of photons that satisfy certain conditions, and then you detect one, and then you do whatever you want with the other one. And so generally speaking, so for each of these kind of sources, there are an array of figures of merit. A lot of them are implementation specific. But for the purposes of this course, we can work with some very broad kind of figures of merit, which first of all is how good is the single photon? And we can talk about what that means a little bit later. But most of the time, what we mean is that it really has to be a single photon. It can't be like n equals to 2 Fock state, for instance, right? In the mode that you want. You don't want that, or it can't be like a coherent state for whatever reason. And the other thing is that you need to be able to interfere them. So ideally, you need it to be indistinguishable. And furthermore, there's the matter of loss. And there are a couple of things to consider when it comes to loss. The first thing is, since we're assuming we're working in optical fiber networks, what's the loss as it goes through the fiber? That's just something that we always have to consider. The other thing is whether or not we can extract these photons that are generated well. And I think there was a question in the Q&A a little bit earlier about either quantum dots or color centers while Marko was talking about methods for coupling. And then the next thing, very broadly, since we're insisting that we must integrate these single photon sources onto some kind of platform, we need to make sure that it's actually worth doing, which means we need to make sure that it actually does scale well, because, if you make 1,000 on a wafer and only one works, then what's the point? You might as well like make one in bulk that works like at a higher rate, right? I'll first start talking about deterministic single photon sources. I will go into detail in quantum dots and then briefly talk about color centers at the end. At the end of the day, when it comes to being a single photon emitter, they behave relatively similarly and have similar kind of pitfalls, etc. Let's think about a quantum dot. At the very basic level, a quantum dot is a sandwich of materials. Well, like you saw earlier when Marko talked about slab waveguides, we are looking at a lot of sandwiches of materials. In that case, in the case of a slab waveguide, what we're interested in is the refractive index contrast between the materials. In this particular case, for making a quantum dot, what we're interested in is the band structures of the materials. And specifically, we want the quantum dot material to have a different band gap compared to the host material. So, so different band gap. So very roughly, this is very, it doesn't take into account all sorts of effects, but very roughly, you can think of the host material having some kind of band gap, and then right next to it is the quantum dot material, and then you have some kind of quantum, you have a different band gap in the quantum dot material. In this case, it's smaller. And then if you look at the top, this starts to look like something very familiar, hopefully. It looks like a finite potential well. That means that what does that mean? That means that if you solve it, you will end up with some kind of level in there. That's a level for electrons in the conduction band. And then if you look at the bottom, what does that look like? Well, it looks like a finite potential barrier. You can also solve it and get out an energy level that's for the whole. And what you generally do when you have such a band structure with these kind of discrete levels, 2 levels in this case, is that you can like blast it excitation with some kind of laser, and then it will drop down, and then you will get out a photon. And then so now let's have a poll question. Given what I've described, this very rough schematic of a quantum dot, what are the parameters that determines the wavelength of the emitted photon? So the first things first, band gap of the host material, band gap of the quantum dot material, shape of the quantum dot, and power of the excitation pulse. And I will run this as a poll where you will select as many of the options as is relevant. Share results. Yeah, so so most of you got that the band gap of the quantum dot material matters. Slightly smaller than the majority of you said that the band gap of the host material matters. The shape of the quantum dot, only 30% of you. Okay, and then yeah. So let's go back. Let's go to the next slide. And so in bold are the options that the things that matter. In general, the rough way to think about this in this very rough schematic way is that if you have a finite potential well or a potential barrier, it is the difference in the band gaps, the height of the well or the depth of the well that matters, and that's a difference in the band gaps. And therefore, what that will do is that, both the band gaps of the host material and the quantum dot materials will matter. Next, the shape of the quantum dot will actually matter also. If you think about different shapes of potential wells, if you solved any in kind of maybe an operative quantum mechanics class, a square well looks quite different from a harmonic oscillator well, and the levels therein look quite different. However, the power of the excitation pulse really doesn't matter. What generally matters is actually the wavelength of the excitation pulse. So with that out of the way, let's kind of give it, instead, let's move on from this terrible schematic to thinking about something real that someone has made. So let's look at a specific material and look at what quantum dots normally look like. So here is an example of a quantum dot fabricated on a gallium arsenide host. The dot material is indium arsenide, and this is before it's capped. And this is an atomic force microscopy image. And the first thing you notice that this thing is extremely small. It's about 50 nanometers wide, and actually height-wise, it's kind of on the order of 10 nanometers, maybe smaller. Yeah, and you can kind of see different ones littered all around, kind of randomly. We'll talk about why that is a little bit later. The shape of it is pretty reflective of what they usually look like. However, you can use a lot of different materials for the dot itself. And depending on what kinds of materials, blah blah blah, that you do use, you'll get emission in different wavelengths, and then you can typically and people do a lot of work kind of characterizing how good the single photons that are generated from these quantum wells are. One of the ways to do it is using an interference measurement. two photon interference measurements, quantum interference specifically. So if you actually have a single photons that are identical arriving on a beam splitter at the same time, you should have max visibility. If you're not quite single photon, you'll erode your visibility. If they're not quite the same, the visibility will change. And so here's a summary from a nice review paper about where the wavelengths of various demonstrations of quantum dots that exist occur at, and also the interference visibility. And I would encourage you, after you receive the slides, to check out the review paper. It's a very nice one. And so it turns out, and what we can see from this particular graph is that the best performance happens in the 800 to 1 micron region. This is where it's the highest in terms of interference visibility. However, and also they, this is something that's not in the plot, but in general, they use relatively standard 3.5 semiconductors. So gallium arsenide, indium phosphide, etc. And then the one last thing to note is how they are made. These structures are often grown epitaxially on a host substrate. These things are generally way too small to actually reliably make using lithography, I think. So usually what happens is that you grow it layer by layer. That's what's meant by epitaxially, and then by growing a material up to a certain thickness, it'll accumulate some strain, and then at some point it'll start forming islands, little tiny islands. Usually this baseline process is called self-assembly, 3D self-assembly. And so usually, you kind of just stick the material in and then do some kind of vapor deposition with very finely controlled parameters, and very slowly. The kind of a little bit more kind of advanced way of doing it, it's not quite clear. Well, okay, so from the left side, you can actually see, like, you have a quantum dots, and then like people are already putting, some kind of other nanophotonic structure in it. So actually this is, in general, quantum dots by its very nature, quite naturally part of the integrated photonics ecosystem. But on the right-hand side, you kind of have a different way of growing these quantum dots. I didn't put in a name here, but you can see this thing called DE QD. That DE stands for droplet epitaxy. And what that means is that during your growth, instead of growing a lot relying on 3D self-assembly, which to kind of grow these little islands, what you do is you first let droplets form on the surface, and then you anneal it, and then they crystallize, and usually they have better shapes and you can make them bigger. And then so in general, with this primer on quantum dots and a rough idea of how they're made, let's think about the figures of merit that we discussed earlier, which is, well, the quality of a single photon. Well, you can't really get better than near unity quantum interference, right? So yeah, so they're great. What about loss? Well, within the material, presumably the loss is fairly low. Of course, like Marko said, the material itself, has some kind of inherent loss. Semiconductors are usually a little bit higher than other systems. But you can imagine putting these quantum dots, integrating these quantum dots like heterogeneously or hybrid with other a lower loss material. But as you can see from this plot, actually, the best performing quantum dots are not in the optical telecommunications band. And in fact, the ones that are way over in the optical telecommunications band, well, first of all, there are only two, and they don't look so great. And then how about scaling? Well, these are pretty standard 3-5 semiconductors. You can get wafers of them. Epitaxial growth is like fairly expensive and slow, but any kind of foundry or whatever clean room that does any kind of 3-5 semiconductor for classical photonics will be doing that in any case. So it's actually it's a fairly standard process. But yeah, so it seems like everything looks great. Why even consider other types of emitters? Well, let's play devil's advocate a little bit, and then let's consider a few. Let's consider the following. If you must use a quantum dot as a single photon source in your integrated photonics platform, what is your biggest concern about it? So I have 3 options for you. The first 2 are about loss, and then the last one is about scaling. So I'll launch the poll, and then you'll get a little bit. Okay. Okay. Here we go. Here are the results. So it seems like folks were most concerned about the scaling. I think folks were a little skeptical about whether these can be made indistinguishable, despite my alleged claim that you can make these in wafers, so of course it's scalable. And then next, people were concerned about sending these through optical fibers, and then only 4 of you were concerned about the transparency windows of the material. And so this is another one of those questions I have in this slide deck. Actually, most of the questions in this slide deck are like this. They're a little bit open-ended. They're there to encourage you to think. So depending on your knowledge of the field and like which part of the kind of general like quantum information kind of or like photonics field that you're looking at this problem from.
People cannot see results. Can you share results?
Oh, I shared the results. Wait, hold on. I did share the results.
They can. Okay. They can.
Okay. Yeah. So depending on like where you are coming from, and in the field, and obviously like people will argue about this. You'll have different concerns. But my biggest concern is this one, scaling, which is most of you. Just because if you just look at these kind of how they're usually made, first of all, your critical dimensions are extremely tiny, and the growth process, because first of all, it's for the self-assembled case, there is inherent randomness to it. Both in where they form and also like how they form. Local conditions might change their shape a bunch. And then secondly, in the droplet kind of method, it looks a little bit more controlled, better controlled. But location-wise, it is still not great. And this is actually an active problem that people who work on quantum dots are trying really hard to resolve. So a lot of these problems in quote unquote problems in various types of devices are about how to make these devices well and repeatably. Usually you show like really high specs for one device, but the thing that but people are actually also, for it to really become technology, you actually need to be able to make it repeatedly many times. So this is an active area of research. It might change forthcoming. But in general, what this means, the randomness means is that every quantum dot you get is kind of like a slightly different wavelength, and then like you interfere them. Well, it's kind of hard without a lot of active tuning. The other thing also is that the random locations makes it so that like if you want it specifically around a certain like nanophotonic structure on your platform, there's some luck involved there. Usually you can control the densities of the quantum dots, which helps you out a little bit, but you can always get really unlucky. And then finally, the other thing that folks were concerned about, which actually I didn't even think about, well, I did think about, is sending these photons through optical fibers with low loss is something that people were concerned about because they're emitting not in the optical telecommunications band. I guess one of the things that people are trying to do actually is to do wavelength conversion using second order nonlinear optics effects or third order nonlinear optics effects to convert mostly second order nonlinear optics effects only actually, to convert these photons down to 1550. So you'll hear about second order nonlinearity later in my talk as it relates to actually sources, but these things are actually also one part of the kind of a quantum network if you want to base it on an incompatible single photon source that will be very crucial. These frequency conversion modules. These are classical actually, but well, they can be described classically, that is. But we won't talk too much about it here in the main text. We might, if we have a little bit of time left over later, maybe we can talk a little bit about it. Though it's looking unlikely that we'll have extra time given that I don't have that much time left. And then the last one, which people were generally not super concerned about, was transparency. And I have a little thing here that says, yeah, you shouldn't really worry about it. You can get losses like comparable to silicon on insulator. So if you want it to be basically comparable to silicon, then you're actually just fine. You're doing just fine working with a 3.5 system. So here's a quick summary. There's all your figures of merit, and then some things to think about. And yeah. And then the other type of atom-like systems in solid state materials that we want to think that we can use as single photon emitters are diamond spin qubits. Marko, do you want to talk about this one? Hello, Marko.
I do. Just trying to find the buttons. Yeah. So maybe you can continue sharing, and I will just go through this and tell you what to go next, right? So
yes,
so
sir.
Spins qubits are another very interesting source of single photons, but in particular, they're interesting not only as a source of single photons, but as actually as a quantum memory. And so this was going to be animated, but unfortunately is not. But anyways, this picture in the middle shows diamond crystalline lattice, and basically what you can blue balls are carbon atoms. What you can do you can basically, the way you form these defects, these are so-called color centers. You remove, for example, one carbon atom and replace with nitrogen using, let's say, process or ion implantation, or maybe it can be done during growth, right? Where you're growing diamond, you can introduce some nitrogen. And so on the left, if nitrogen takes position on carbon, and then if also nearby carbon is also missing, that forms so-called nitrogen vacancy color center, which is one of the first color centers that got prominence. And by the way, there's well, maybe not millions, but there are books published on diamond color centers, and there's very many of them, and they are very well known to gem industry because they use the color diamonds actually. And so in nitrogen vacancy color center was first considered as very nice quantum memory, and the reason is that it has electron, when it gets a negatively charged, electron spin associated with it actually can be spin of electron that's associated with the nitrogen vacancy color center can be used as a qubit. And what's really important in the context of this presentation, in the context of technology, it actually is can be optically read out and optically controlled, right? So the problem with NV center, and original reason why the NV centers were really, really interesting, or diamond was interesting, because diamond is very pure host. It's very simple host, just one atom. And the NV centers are really stable. It's like atom-like emitters in solid state. That's how people refer to them. Unfortunately, because of diamond's very high refractive index of 2.4, diamond, actually, most of the light that these color centers emit never leaves diamond. Only about 5% leaves diamond. And that's why you need to actually not make some photonic devices like waveguide or resonators around these devices, around these emitters. And unfortunately, the problem with NV is that when you do that, actually NV becomes unstable. And the reason is that charge fluctuations on the surface of, even if you make perfect diamond waveguide, dangling bonds, charges on the surfaces are strong enough that they can actually result in so-called spectral diffusion. So emission of color, this color center becomes very much not atom-like. It starts drifting all over the place. And so, which is why people started looking into other color centers in diamond, and one that's particularly prominent these days is so-called silicon vacancy color center. So this is silicon atom that sits between two missing carbon atoms, and that atom actually does not have, this center does not have as good spin properties as nitrogen vacancy. Nitrogen vacancy, you can access its spin even in room temperature. In the case of silicon vacancy, actually, it's very sensitive to phonons, so you need to cool it down to millikelvin temperatures to be able to access it, but it's a lot more stable, a lot more robust, even in nanostructures. And so that's why it's actually being explored as a workhorse of quantum repeater effort in CQN and also in general in the world. But long story short, the choice with color centers in diamond at the moment is good spin, bad emitter, or good emitter, bad spin. So the search is still out for best of both worlds, and that's something that we are actively pursuing as community. Next slide, CJ. Probably we should skip next one, which is silicon vacancy detail, and maybe just go to two.
Yeah. Before we move on to the next slide, there are a couple questions that
Yes.
maybe you'll have fun at answering live. The first question is, can diamond qubits be achieved in thin films in photonic integrated
Absolutely. So
circuits?
this is very much something that we do in center, like my lab, Dirk Engel's lab. Probably I'm missing a bunch of people in the center. And diamond thin films are one of the ways to actually make photonic structures in diamond. Unfortunately, unlike silicon on insulator 3.5s and whatnot, diamond on insulator or thin film diamonds are not readily available. And so we as a community have come up with different ways to make devices in diamond, bulk diamond, but thin films are becoming much, much better actually these days. In particular, work from Alex Hai's group at Chicago comes to mind lately.
And then there's another one. Are these kinds of color centers more scalable relative to the conventional dots?
That's an interesting question. So I would go with yes. And the main reason is, well, it depends what you want to do. Diamond color centers, they are dimmer than quantum dots. So they're not, as a single photon source, maybe not ideal, but they can be positioned deterministically. And so we use ion implantation. In the past, we used so-called focused ion beam implantation. That's collaboration with Sandia National Labs. More recently, we actually implant through apertures. And so you can place color center with precision maybe 40 nanometers XYZ, essentially the center of optical cavity. In the case of quantum dots, the best quantum dots are randomly located, so you need to find them and build a device around them. So in that sense, this is a little more scalable. The diamond color center is a little more scalable. But material itself is, smaller. You can get 3/5 in, I don't know, 2-4 inch, maybe 6-inch wafers. Even diamond size is, I don't know, centimeter scale. So it's depends which aspect of scalability you're looking for.
Okay, so you said to skip. There's still a few more questions, but I think maybe Marko, do you mind taking care of that while I?
Yeah. Absolutely.
And maybe then, when I start talking about probabilistic sources, maybe. Yeah. So next slide.
Show cavity, maybe.
Then, yeah.
Yeah. So basically, this is kind of the workhorse of activity in CQN, and also we have collaborations with other group. This is in particular collaboration with Michel Lukin's lab. Dirk Engel does very similar work. So here what you see is diamond waveguide that is perforated with holes. These holes are used to provide mirror for light. And as a result, this is so-called photonic crystal cavity I mentioned briefly. And as a result, you can trap optical mode shown with these, it's actually composite image, what you see here. Blue and red blotches are basically numerically obtained mode profile of one of the modes of the cavity. And we implant silicon vacancy, whose structure is shown above, right in the middle of the cavity mode. This diamond fabrication is very non-standard at the moment, but it can be done in thin films, as somebody asked. And then another nice thing is going back to what we talked about earlier, bringing light on and off chip. Like if you have single photon and all information is embedded in single photon, you better do not lose that photon. So we need to have 99.9% ideally coupling efficiency to optical fiber. And the way we do this is take fiber from like 100 microns diameter, we taper it down to point basically, and then bring this point to a diamond waveguide and touch it. And then you have now these evanescent fields of optical fiber and diamond waveguide. They kind of couple and make a directional coupler that is tapered. So that allows light from the fiber to be extremely high efficiency, hop onto diamond, hit the cavity, bounce back and go back to the fiber with, like, as I said, 99% or so. 0.15 dB is, I think, at the moment, coupling efficiency per pass. And then that allows you to essentially make various gates by coupling silicon vacancy strongly to optical cavity and coupling cavity to the fiber. So maybe I'll just stop here, CJ, and you can take over.
Okay. Yeah, I'm still sharing, so I'll just start talking then. So after all that about deterministic single photon sources, we're going to start talking about something that sounds strictly worse. Which is probabilistic single photon sources based on optical nonlinearities. And usually these are called heralded single photons. I'll step through really quick what the process for generating a heralded single photon is. And then there'll be a little question at the end about why it's probabilistic. So first, what you have to do actually is just to pick a material with second order nonlinearity. You inject a strong pump into the material, this one, or pumps if you're using Chi3, and then there will be a parametric nonlinear process that will generate a pair of photons that satisfy energy and momentum conservation relations with the initial photon. What it means by parametric really just means that you're not actually exchanging any energy and momentum with the material. Yeah. And then the thing to really note here is that the resultant photons, they are always generated in pairs. If there's one on one side, there must be one on the other side. So after they're generated, what you do is that you will separate them into two modes. Usually it's spatial modes, because that's easy. And then you pick one of the modes, and then you detect the photon in one of them. And assuming ideal conditions, no loss whatsoever, you have now guaranteed the existence of a single photon in the other mode. And so what you can do then is that what you can use the detector click in the heralding mode, this one, to post-select for successful operations on the single photon in the heralded mode, the red one. Basically what happens here is that you're pumping with some kind of clock rate, you're doing operations with some kind of clock rate, and then you measure the results of that operation, and then afterwards after you have everything, you say, okay, these were the ones where the heralding detector actually clicked, so these are the only ones that are valid. Or you could use the detector click to control what happens to the heralded photon, and that actually requires all of the processing. So that actually requires your signal to propagate fast enough to reach whatever thing you're trying to operate on the other photon with. And then it also requires that that element also operates relatively fast. Yep. Wait, oh, okay, this is a repeat slide. Now, after, I've gone through this gory slow detail, this entire workflow generating a heralded single photon source. Could you please tell me why I call this probabilistic instead of deterministic? Can you indicate the step where the probabilistic part is happening in the poll? I hope this is a review from previous sessions, but yeah.
CJ, want to answer the question? Can probabilistic source generate entangled pair of photons that we can use?
Yes, absolutely. Yeah, one of the nice things about these kinds of sources is that you can either use them as heralded single photon sources, or you can use them as entangled pairs. Actually, in some cases, it's really easy to generate entanglement between pairs, and in certain degrees of freedom, and what we try really hard to engineer it out, because we prefer it to be not entangled, or we prefer it to be entangled in another degree of freedom instead of that one.
Related question, this is loaded one. Would you call single photon emitters from color centers in diamond deterministic or not?
Oh, that's interesting. I had left one as a fun one for you, but
yeah, I can answer it. I mean, it's yeah. I'll give you my perspective. I mean, the photon emission rate of diamond is not very large, so, and if collection is not very good, even if photon gets emitted, you may not see it all the time. So, does it get emitted every time? Yeah. Do you get to see it? Maybe not. So, I don't know. How would you call this, CJ? Non-deterministic, I guess. I don't know. I mean, it is.
I would actually call it deterministic, because in the ideal case of no loss, it is deterministic. Whereas for these sources, there is a fundamental reason why it's probabilistic, which we'll talk about. Yeah.
And also, Spencer,
that's just my take. Sorry.
Spencer Dimitrov want to ask a question again. I accidentally hit answer live, but it's not answered live, so I cannot answer it. Sorry.
Okay. Okay. Whoops. I left it running way longer than 2 minutes. But let's end the poll and share the results. So most of you clustered in step 3, which is, this is one of those rare questions here I have that does have a correct answer. It is 3. My intended answer was 3, but let's back up and see. Injecting a strong pump into the material in generally it's not, you don't really have a probability there unless something's wrong with your source. Number 4, separating the pair into two different modes. Actually, that one can be probabilistic depending on your implementation, especially if you aren't able to separate them into two different modes. you can just put them into a regular 50-50 beam splitter, and then like you'll only have them separating like half the time. But that's not one of the assumptions that I was making here. So I can see why that might be one of the answers. And then there's 5 detection. Yes, detection is probabilistic if you account for quantum, if you account for the efficiency of the detector, similar to the idea that we were talking about color centers. Are they deterministic? Are they probabilistic? You definitely, even if you always have one photon, you might miss it because your detector isn't perfect. But in this case, we're talking about a more fundamental kind of probabilisticness, probability in a sense. And then number 6, yeah, if your devices were imperfect, yes, that could occur with some probability. But strictly speaking, if we assume all perfect components, classical components, all working perfectly, the only thing that's fundamentally probabilistic is this parametric nonlinear process ability to generate pairs of single photons. So let's take a look at why I keep insisting that it is fundamentally probabilistic. And to that, I'll take a pedagogical approach, as Marko would like to say, but basically there's a lot of gory detail. Basically, let's look at the probability of photon pair generation, and specifically probability of a single photon pair generation, by which I mean you generate a pair and there's one photon in one mode and one photon in the other mode. So let's make a lot of simplifying assumptions because the actual formalism gets pretty gnarly really, really quickly. Let's just assume a Chi2 parametric down conversion process, which means you have a single pump and then you emit 2 photons. And then so let's call initial let's assume that we know like which modes these are. And then each one mode we label as A, one mode we label as B. I'm just going to state without proof that the Hamiltonian for this PDC process is this form. And in this case, you have the ladder operators for creating photons in your signal mode and your idler mode. And then you have some coupling strength zeta at the top. And then if you're interested in why this is happening, you'll have to do EM field quantization in a nonlinear medium, which you can look up some texts on, or wait, no, the thing to say is left as an exercise for the audience. So if we define it like this, right? If we say, okay, eventually, if we focus in on these 2 modes that we know photons will be emitted into, let's take about what is the initial state? The initial state, well, there is the pump, but because the pump is a strong pump, we can treat it classically. So classically, you treat the entire, you can treat the entire material and strong pump as and lump everything about the material property and the pump into this coupling strength zeta in here. And so initially what is the state is actually there are no photons. And I'll indicate this. This is sometimes called a vacuum state. Sometimes it's indicated with like a bold phase 0 or vector 0 in here. But and then what you do is you use the Schrodinger picture, and then you propagate the you try to figure out what the state is, the final state is after interacting with the medium. So the form of the final state looks like this. The operator here acting on the initial state is e to the minus IHT over h bar, which is just Schrodinger's equation. And then this is the part where you do, I skip a lot of steps in the math, but you do some substitution. Yeah, you put that Hamiltonian in. And then at the end of it, if you do out this exponent and apply it, what you'll end up with is the following. so you have a hyperbolic secant right up here and then r with the argument r, and then you have a summation of this coefficient, which is raised to n, where n is the number of pairs, number of photons in each mode that's generated. So basically what this says is that when in the final state, if you make a measurement of how many photons there are, you will always find the same number of photons in each mode. And it turns out that it is not just putting out single photon pairs, it's actually putting from 0 all the way to infinity. And then if you recognize, I think there's some ordering issue with the slides. Sorry for the delay. Yeah, so this one. So here we can make a few observations. The final state is actually what we call, has a name. The form has a name. It's called a two-mode squeeze vacuum state. The parameter R is a function of interaction strength and interaction length, which, interaction length, interaction time evolution. And then the parameter zeta, which I keep calling interaction strength, actually absorbs in all of the parameters, like pump power, a bunch of parameters actually, like pump power, the effective nonlinear coefficients of the material, and also mode overlap, which in waveguides you really care about, because and roughly speaking, basically, is that your interaction strength will scale linearly with power. It'll scale linearly with nonlinear coefficient, I believe, and then I think, yeah, the mode overlap ends up being some weird, because there are 3 modes, it ends up being a little weird. It ends up having units of 1 over area, or something like that. And we call it an effective area, and the effective area, like the smaller it is, the better it is. And the final observation is actually in this way that we've treated it by making these assumptions about, like, we know what exact modes they're emitted in. It's not terribly obvious where the energy and momentum conservation conditions are coming from. But in order to actually figure out where the energy and momentum conservations are coming from the Hamiltonian, you actually it's actually easier to look at it using first order perturbation theory, which we won't do here, but there are a few references that you can look up if you are interested. Anyways, so after this little aside about all these things about the gnarly math and deriving the final state, what we do is we use the final state and we calculate the probability of there being n photons in each mode. It's terribly phrased here, but what I mean is that, like, they have the same number of photons. They always have the same number of photons, and when measured, and how many photons there are in that mode. So it's a probability. You know how to take a expectation value of a measurement. And then so if you plot it out, your probability of having 0 is 0, which means that you are returning the vacuum state. Nothing happens. You actually end up with a fairly high probability across the board in the blue curve. And then n equals to 1. Yeah, you end up with, like, the more than 50% probability of returning vacuum all the way until, like, R is greater than 0.88, which we never quite go that high. And then there's also the probability. You also have the probability of getting a single photon pair. it's in the orange, and then you see it goes up. It doesn't go that high, and then it starts turning over. And the reason it starts turning over is because the probability of there being more than one photon in each mode starts becoming appreciable at modest r. And so this is summed over the probabilities of all the n's all the way down up to infinity. So yeah, it goes up really high. And in this case, what we note is that only the 1, the orange, is actually useful for heralded single photon sources. Now, if you actually drive R higher and higher, the two-mode squeeze vacuum state can also be useful for certain sensing applications. Actually, about 2.0 here is about like probably like 15 dB of squeezing, which is you know, if you can do it, you'll get a lot of money from funding agencies. Yeah. So now after all this about the probabilistic single photon source, I have another full question for you. It's a little bit of a two-parter. The first part of this question is, where's the, the first part of this question is, for generating photon pairs to be used as heralded single photons, is there an optimal pump power to operate at? Yes or no? And then the next question is, for generating photon pairs to be used as part of a heralded single photon source, what is the optimal R squeezing parameter to operate at? So first, your optimal R is when, and then, well, you can just read the options. And I will launch the poll right about now. You get 2 minutes. Alrighty, that was 2. 55% of you still participated. Thank you. This is when we usually start, or I would expect to start losing people. But for question 1, the majority of you answered yes. The 3 of you answered no. And my answer actually to this question is, this is kind of a trick question. And you'll understand a little bit why, because I asked the second question, which asked about the optimal R, which actually doesn't look quite right in the poll. But the question is not quite right in the poll, but the options are. But the optimal R, about only 2 of you said that. So that one does have a correct answer, and that is, you can make an argument for the second one or the third one, but never for the first one. And the reason for that is because the probability of more than 1 photon in each mode, when that probability is minimized, the probability of emitting 1 photon is also 0. It's actually right at the origin here. So that can never be the answer. So about 15 of you answered that you want to maximize the probability of exactly 1 photon in each mode. And actually, that is a valid answer. So if we look at this plot, if you are able to measure, when you make a measurement, if you're able to tell how many photons you're measuring in the heralding channel, then you can say, okay, I measured 1 photon in the heralding channel, the other one is useful, or I measured 2 and then the other one's not useful, so you can operate here. But that requires your detectors to be photon number resolving, which actually tends to a kind of a more exotic type of detector, all told. And it's recently seen a lot of development, although I'm learning that my sensor recently is starting to get distorted, because 10 years still seems very recent to me. But yeah, so you can make an argument for option 2, being the optimal R to operate at. But actually, in a lot of cases, what you're working with is option 3, where you really have to make where you really have to make a hard decision about do you want more single photons, but also more single pairs, and then like but some probability of multi pairs, and then or you can quantify that by plotting the ratio of how many single pairs out of all the clicks that you receive are how many clicks out of all the clicks that you receive correspond to single pairs, and that's how you would plot this. You can see that it just straight up declines. There's no like peak or anything. So you usually say, okay, for this application, we can tolerate like this amount of multi-pair, and then you say, okay, then I will pump at some R, right? But it ends up being a application specific kind of answer. And I see in the Q&A, someone said, yes, does the power, wait, no, never mind. I misunderstood the question. Never mind. Don't worry about it. But okay, so let's now get back to the first question, which is there an optimal pump power to operate at? So you can argue both ways. You can say yes, because if you assume a constant interaction length, constant nonlinearity, and then you want to get to a certain and constant mode overlap, and you want to get to a certain R, because there is an optimal R, then there is definitely an optimal pump power to operate at. However, because the thing that needs to be optimal is how large your R is, and R actually from over here depends on a bunch of different parameters. So let's say I could, if my pump power, if my mode overlap, I engineered it to be better, or if I used a material with higher nonlinear coefficient, actually my optimal pump power would change, because what I need to optimize for is the squeezing, not really necessarily the pump power if we can change the other parameters. So that's why it's kind of a trick question, because usually you're working with some kind of fixed nonlinear coefficient and mode overlaps and that kind of thing. So it actually just translates to a pump power up. The optimal in R just translates to a pump power optimal. Okay, skip over. So far, actually, we have proven to ourselves that there is something just inherently probabilistic about like whether you're able to measure out single photon pairs, just because of how that vacuum state evolves after it passes through the when it interacts with the strong pump and nonlinear material. Well, does that mean that, well, these sources are just kind of worse in every way? Well, obviously, since I'm spending so much time talking about it, the answer is actually no. And the reason for it is actually pretty interesting, is because as much as people have poured resources into deterministic single photon emitters, when you actually want to do like a very ambitious demo, for instance, some kind of large 12 photon entanglement boson sampling. This is work by Jianwei Pan's group back in 2018, which is 5 years ago. You end up resorting back to your SPDC, your probabilistic, in this case, parametric down conversion sources again. And a funny thing here is it's really small. But when they uploaded it to the archive, the comment was, "This is the Make SPDC Great Again paper," which interesting humor. So there must be some advantages, right? Like if people are using it so much. Well, and the reason is actually this. These sources end up being much more versatile in terms of emission wavelength and bandwidth. And we will talk a little bit about why. But roughly speaking is because you generally are not, you generally can turn this into a problem of engineering the device structure and geometry rather than engineering the material, engineering a device because we're really good at microfabrication because of semiconductor reasons, tends to be easier than doing materials engineering, or drastic materials engineering for nonlinear optics. And the second reason is you don't need to operate cryogenic temperatures. Strictly speaking, you don't necessarily need to operate quantum dots, or you can operate them a non-cryogenic operation, but it's generally better. They work better when they're cold. And then when it comes to bulk sources, actually, it's easier to make large arrays of identical sources. Because why? Well, if you're using a bulk source, actually, usually it's just a block of crystal of a certain length, right? Your length is measured in millimeters or whatever. The tolerances there are enormous. Like, you don't really have terrible tolerances there. So you can like buy 12 of them and set them up. Of course, you have to align them properly. So a lot of labor goes into it, but then in terms of actually manufacturing the source is relatively simple to make. So, there are some advantages. It has to do with temperature. There's some fab thing, manufacturing thing associated with it, and then there's this wavelength and bandwidth versatility, which I will spend a lot more time on. Why is it that these probabilistic single photon sources are kind of have a lot of wavelength and bandwidth versatility? One of the reasons is that well, you have a wide range of nonlinear materials that are just in common usage. You have your choice of second order nonlinearity, which restricts your subset of materials a little bit to materials that are non-central symmetric, because the Chi2 nonlinear optic tensor has a particular symmetry depending on the material. So your material needs to lack a certain symmetry, otherwise it will cancel out and become zero. But a lot of them are available. If you read the literature, a lot of experiments use beta barium borate. I actually started my quantum optics lab work using beta barium borate. You have potassium titanyl phosphate, KTP, and then you have Ln lithium niobate. And then if Chi2 doesn't do it for you, you can use Chi3. It's much weaker. You'll need 2 pumps, strong pumps. So power requirements start getting to an issue, but we know how to make some really good, like, high power lasers, and if all else fails, you can use an amplifier on the pump, right? And it might be worth it because it's much less symmetry limited. And usually for integrated photonics platforms that have very, very low material loss, like silica and silicon nitride, it still exists and you can use them. So that's one things. The other reason that wavelength and bandwidth versatility, you have a lot of that wavelength and bandwidth versatility, is because the signal and idler pair can have any pair, because of the energy and momentum conservation. Your signal and idler pair can basically have any combination of frequencies as long as that is fulfilled, and that ends up being pretty easy to fulfill. So let's look at energy conservation. So what that turns into, strictly speaking, is that your pump energy, your single photon energy of the pump must equals to the sum of the single photon energies of the generated photons. Well, in that case, you can just, if you want a specific frequency or energy of your signal and idler, you just choose your pump accordingly, right? we have good lasers at a lot of wavelengths, and specifically in for fiber optic communications, you're usually trying to generate kind of signal and idler photons near or around 1550, and that means for Chi2 you're usually working at with a 775. You have a number of options there. You can use a TISA. They operate really well there. Or if you're using Chi3, actually your pump would just be near 1550. And because so much, there's been so much invested in telecommunications, you have a lot of really good lasers in the telecommunications band. And then the next thing is momentum conservation, which we often call phase matching. And it simplifies to your momentum of the single photon pump must sum to the momentum of the generator photons. These are vectors if they are not propagating non-collinearly, but then if they are propagating collinearly, that means the pump, signal, and idler are all propagating in the same direction inside the material while it's interacting, then these are actually just scalars. This is a phase matching problem, and it's mainly an issue for Chi2. And it turns out that there are a lot of ways to do phase matching. You can rotate the crystal so that the light sees the ordinary, one beam sees the ordinary optical axis, the other one sees the extraordinary axis, and then anything in between. But by far the most versatile method in this class is quasi-phase matching in ferroelectrics that also have strong second-order nonlinearity. And the prominent examples of this are potassium titanyl phosphate and lithium niobate. And what this does is that it turns fulfilling this phase matching condition into a device engineering problem as opposed to materials engineering problem. If you don't use quasi-phase matching, you're actually dealing with a materials engineering problem, because the reason the phase matching condition is not fulfilled is because you have some kind of material dispersion. What quasi-phase matching is that actually you take a material, right? And then you apply a strong electric field in one direction that's opposite to the spontaneous polarization of the material. And then periodically, you flip your material crystal orientation. And what that does in the second, in a non-central symmetric crystal for the relevant second-order non-linear coefficient component is that the sign of it flips periodically. And you say, okay, let that period be equals to 2 pi over the phase mismatch. So basically, what this does is that it introduces a grading. When you think about grading structures, it always introduces an additional momentum kick. And what you're doing is that you're using the geometry to add the momentum kick that you need to fulfill the phase matching conditions. And it turns out that fabricating these, while kind of difficult, has been worked on since 1998. We know how to do this in bulk really, really well. And in general, the feature sizes are not too small. They're like tens of microns for photons generated in telecommunications. So the fabrication tolerances are just kind of like you close your eyes and you can do it generally if you have access to photolithography. And so that is how you can generate photons. You can basically almost freely choose where you want your heralded single photons to be generated. In this case, 1550. It's basically trivial to do it. And then there's a kind of a deeper level to it, which is you can actually also engineer the bandwidth of the photons. And not only can you engineer the bandwidth of the photons, you can actually engineer the correlations between in the temporal spectral degree of freedom of the two photons, right? So normally if you generate, if you have two photons and then you say, okay, okay, it's one frequency, you can't say that whether the other photon is a particular frequency or not. But in the case of single photon pairs generated from these kinds of nonlinear sources, you sometimes can get that. So usually how we visualize it is we visualize the energy conservation condition right on the left here using a pump envelope function. And basically this anti-diagonal line here with some kind of width is, this is just a pump, and then the width is the pump bandwidth. And then on the horizontal axis, you have the frequency of the signal, and then on the vertical axis, you have the frequency of the idler. And then basically this shows, okay, by energy conservation, what probability is allowed here at each combination of points. And then you also visualize the phase matching. The phase matching slope can actually be any number of things, depending on group velocities, the group velocity mismatch of your three of the three modes involved, and then you can plot the momentum conservation of phase matching condition like so. That says if we impose phase matching, which combinations of wavelengths are allowed. So at the end of the day, the combinations of frequencies between the signal and the idler that are allowed will have to be both allowed by the pump and both allowed by the phase matching. And so you multiply these together, and lo and behold, you get two different shapes. This one just kind of looks like a non-rotated kind of Gaussian. It's a little stretched out a little bit. But this one, actually, you can factor the frequency. So in a sense, you get no information about the frequency of the other photon if you measure one of them. However, in this case, it ends up having a very high positive linear slant. And so basically you start getting information about, if you detect the frequency of one of the photons, you start getting information about the other one. And depending on your use case, it's one or the other. But usually for heralded single photons, you want it to be spectrally separable. So then figures of merit for these photon pairs in bulk. Quality of a single photon. It depends on your chosen operating point, your pump power. There's an inherent trade-off between purity to a single photon state and a pair generation probability if you're using click no click detectors. Actually, even if you're using photon number resolving detectors, there's a trade-off. And then for spectral purity, which means for heralded single photons, you generally want there to be no entanglement in the photon pair, because usually your detectors are also not frequency resolving. You need it to be spectrally pure, which means you need it to be this kind of non-slanted Gaussian. Your biphoton spectrum, joint spectrum needs to look like that and not slanted like this. And then next, loss. Well, your material losses are pretty negligible, and also it's trivial to generate optical band. You're pretty much doing way better here. And then for scaling, well, I guess you can buy a lot of them, and if you spend a lot of labor, you can make really large arrays. However, the scaling of the footprint, really, you can't avoid. It gets pretty unmanageable pretty quick. So that's for bulk. So for bulk, you already start seeing glimmers of why they might be preferable to deterministic single photon sources. Is mainly the loss issue and the scaling issue. But okay, yeah, let's put it into an integrated photonics platform. It is based on optics. It's just natural. It seems natural to put it in an integrated photonics platform, right? And indeed, people have gone about putting this in all kinds of different materials. You have 3.5, which required a little bit of a kind of finagling to get a waveguide. They actually made a waveguide out of Bragg reflectors. Turns out gallium arsenide also has is also second order, has a non-zero chi2. You know, you start putting you make a ring in a chi2 material, and then you let SPDC happen in the ring, and then you couple it out. You know, you start seeing like quote unquote integration with some passive devices like couplers, WDMs here. This is an aluminum nitride, which I think we so far haven't mentioned. No, Marko mentioned it. And then you can play around a little bit and you can do it in lithium niobate, and actually you can do engineering of the joint spectrum by introducing additional waveguide dispersion. And then so normally lithium niobate will give you a very like slanted kind of joint spectrum, but then once you engineer it, you can get it like kind of relatively separable like this. And then chi2 aside, you have your really low loss systems. You know, you can do four-wave mixing and silicon nitride. These have amazing Q factors. You also have silicon, which you can fabricate, which, you know, you can fabricate systems really well. You can make these really long kind of SF spontaneous four-wave mixing. And then in this work, I think by virtue of the way they pumped and also the way they engineered their source, they were able to get spectral purity that's almost unity. So very useful for heralded single photon source. And finally, you know, it's kind of debatable. You can argue whether this is, you would count this as integrated or not. But people have been able to make arrays of up to 18 on silicon, and then they picked 5 of them, and then they interfered them, and the interference visibilities were okay. And so basically, in summary, they're generated in a wide variety of platforms. It seems that heralded sources based on some spontaneous four-wave mixing demos are the closest to what we call high quality, which means they have good interference visibilities, and also scalable because you have a demo where they made a large array. No. And the demos are mostly done in telecom band because why not, right? It must be noted that this large array kind of demo was invisible. It was at 730 something, which is also another wavelength of interest for kind of if you're trying to work with interfacing with quantum memories, like the color centers that Marko was talking about. Those are, well, the leading ones are 600, 737, that kind of thing. But you know, it seems like we're not getting much integration or scaling. Like you don't have it much combined with very many components for SPDC. You don't seem to be making people don't seem to be making large arrays of them and doing anything interesting, as far as I'm aware. And that hints at some kind of scaling pitfalls, or I think it is because of some kind of scaling pitfalls. For this, you can recall the advantages of a bulk probabilistic single photon source compared to atom-like deterministic sources is that it's easier to make large arrays because it's really easy to make these sources. You just kind of take a hunk of crystal, right? But it's actually a big asterisk for integrated heralded photon sources because you start shaping the material. That means you start introducing all kinds of geometry parameters that will affect your conversion process and where it's phase matched. So the asterisk, and then also when you start introducing resonators, I'll address that first. Usually for SPDC, you have one wavelength that's really, really far away. And the one that's preferentially generated or enhanced is usually the one that where the pump, signal, and idler, all three align properly. And it's really hard because of material dispersion to kind of make doubly resonant resonators deterministically. It also because where exactly your resonance line is depends a lot on the exact dimensions of your resonator. You can't always get the resonator line to be where you need to be, but it's relatively easy to make thermal heaters. So if that's an option, where the thermal optic coefficient is good, you can use that to tune. And then the other thing is sub-wavelength confinement really exacerbates the sensitivity to waveguide geometry. And this is very, very severe for one of the leading kind of materials, which for in bulk, which is lithium niobate, periodically pulled lithium niobate. In bulk, you can make it fairly easily, but in thin film, you actually introduce many layers of quite a few layers of additional lithography, depending on what you do. In order to pattern electrodes, these ones over here, you can see the ones beside the yellow line, these are all electrodes. To do the domain inversion, and then you also shape the waveguide, right? And basically what happens is that every step of these, every dimension, every geometry parameter of the waveguide can change your phase mismatch of your target, let's say your target process. And it ends up being a nanometer scale sensitivity to the film thickness, because that you can think of it that makes sense because usually in these thin film systems, your film thickness is usually sub-wavelength. So it's the most sensitive to that. So it's so sensitive that usually across a wafer, you can get thrown off by quite a lot from your target wavelength. And also even along the same waveguide, your generation, your effective nonlinear interaction, your R can get eroded quite a lot at your target wavelength because the film thickness is changing along the waveguide. And this is further exacerbated by the fact that this particular material platform, the fabrication is way less mature. We haven't figured out, we haven't made a lot of the mistakes or like kind of had as much as kind of statistics, but this is a problem that I think is solvable by further kind of process flow optimization, etc. In the end, it's not an inherent limitation, it's an engineering limitation. So finally, figures of merit for integrated photonics. Most of them don't change. It depends on operating points, trade-offs, spectral purity, requires filtering or biphoton state engineering, but we now have an additional knob that I showed earlier with lithium niobate, the integrated lithium niobate waveguides, where thin film lithium niobate waveguides, where you can engineer the waveguide dispersion to kind of change the dispersion of the propagation constants of the guided modes. In terms of loss, well, you have some added loss due to fabrication. Usually that's the one that dominates as opposed to material loss, and then but you still can generate things in the optical band. Scaling for a lot of these materials, yeah, you can make it in the wafer scale, but like just because you can make it in wafer scale doesn't mean that it really means scalable, because if the probability of success like drops precipitously, then you might as well make one small good device. But you actually are a little bit less. You're actually a little bit compromised on this front because your device geometry is sensitive. Your device geometry sensitive is way worse compared to bulk. But there's still a little bit of hope, because if you compare the critical dimensions to quantum dots, it's still a fair bit larger. And there's a lot less inherent randomness in the fabrication process, because you're not like relying on some kind of self-assembly during growth, where you're kind of hoping the chemical potentials will just work out the way that you want. Okay, so that about covers it for probabilistic single photon sources. I'm about to talk to blast through single photon detectors next, but before we actually go there, let's take a little aside on actually, if we have probabilistic single photon sources, can we actually overcome the probability? Well, let's remind ourselves what the probability is. We say, okay, even here at where the single photon pair probability is maximized, it's limited to 25%, even with ideal photon number resolving detectors, no loss whatsoever. That is actually just a fundamental limit because of how the process is. You excite it, you pump it once, you're gonna get a single pair, a usable single heralded single photon, maybe 25% of the time out. If you use just one of these, yeah, you really can't get around this barrier. However, you can be pseudo-deterministic, it turns out, if you multiplex many single photon sources. And multiplexing, basically you make a bunch of them all at once, and then you put them all in a switch, and then you use the detector, and then you use it, and then at any point in time, one of these might click, and then you get something out. And then it turns out that the number of, assuming you have these perfect ideal photon number resolving detectors with no loss, in order to get to about 99%, or what is determined to be quasi deterministic, you need about close to 20 sources. You can check out this review paper. Or rather just this paper by Christina Silberhorn's group. Finally, what this means is just by looking at the system, you see that, okay, in order to make this, you actually need a large number of high performance components. And this sounds just like a this sounds like a problem that like integrated photonics is dying to solve, basically. So if we can get really good at making these individual devices, and we can get really good at these classical devices, which actually are progressing way faster, because we're really interested in those. Those have like a way broader range of applications. We can potentially realize like a relatively small footprint multiplex source on an integrated photonics platform. And so here's a summary for probabilistic single photon sources. I've left out all the stuff about bulk here. And the only aside is that there's a high potential for scaling and component and integration in integrated photonics, which means that it's promising for doing multiplexing to reach pseudo-deterministic photon generation. Okay, here we go. Last section, single photon detectors. Well, they're really just two broad classes: superconducting nanowire single photon detectors that basically operate by, you have a superconductor that's kind of operate just superconducting, and then a photon hits it, it gets absorbed, it locally heats up, it becomes resistive, and as a result, since you're passing a current through the superconductor, it becomes resistive, and there's a voltage drop across it, and it emits a pulse. And then over some time, it becomes superconducting again and resets. And obviously, just like what it says on the tin, it uses superconducting materials. The thing is, the operating wavelength is relatively versatile, and there's a very high, almost unity efficiency across a very large range of wavelengths. A lot of the times, the commercial SNSPDs that you can buy, it's not a limitation of the material that compromises the efficiency, but rather the cavity that they put around, where the cavity that they put around the superconducting nanowire is to kind of enhance the interaction. However, superconductors, we don't have a room temperature ones yet, so it needs to operate at cryogenic temperatures, which means that actually, if you want to slap it on the same chip as all of your other components need to be cryogenic too. And well, those need to be characterized. For things like probabilistic photon pair sources, there's, because of thermal optic, where your phase mismatch will change. So those really need to be characterized. People have done it at Paderborn, Tim Bartley's group. And then finally, they can also be photon number resolving. So it really would be kind of the holy grail of let's use these for multiplexing. However, there are also other types of detectors called single photon avalanche photodiodes. We can really just call them APDs. They're just operated at a slightly different voltage. They're operated near breakdown. And the materials are pretty standard APD materials. It will have to depend on what kind of wavelength band you're operating in. Visible for silicon is standard. Telecom, you have a range. InGaAs, indium phosphide, germanium. And naturally, since those are also things that you can make integrated photonics platforms out of, those can be monolithically integrated there. And the really nice thing, and however, these are usually at telecom slightly worse performing than SNSPDs in terms of efficiency. Silicon, they can be comparable, but there are other characteristics like after pulsing and stuff that you have to worry about. The really big boon of this type of single photon detectors is that you can operate them at room temperature. So here's my last question for you. It's an open-ended question. Which one would you choose? And you're going to get 1 minute for this. You can spend 1 minute selecting, and then you can think about to yourself why. Yeah.
Caesar, there's some
And we'll see who
in Q&A if you want to take a look while you're waiting.
Ooh, okay. Oh, there's a lot.
Maybe take a few and then the rest we can.
This is pretty much the end, actually. The rest is like conclusion, which I think was just going to be a verbal riff for you or me. Up to you.
Yeah, you can do it. You're doing a wonderful job.
Okay, thanks, boss. Okay. You said you would like to answer the question about coupling quantum dots into waveguide live. Did you already do it?
I can do that. Yeah, I accidentally clicked that, but I could totally do it live whenever time is opportune.
Now it's good. People are still, yeah. So
there was a question, somebody asked, what's the prospect of coupling, I think, quantum dots to waveguides, and that's, I forgot if it was motivated by my statement that alignment between quantum dot and cavity can be difficult because of non-deterministic location of quantum dots. So you need to find quantum dot, make cavity around it. So what people have done instead, very nicely, first of all, you can use just regular waveguide in 3.5 semiconductor, for example. And then probability of finding quantum dot that's coupled to the waveguide is actually much higher because waveguides are longer than if you have a cavity. But then an important figure of merit in all single photon sources is so-called spontaneous emission factor or beta factor, as well as Purcell factor or cooperativity. They're all related, which spontaneous emission factor tells you which fraction of spontaneous emission goes into the mode of interest, in this case, a waveguide mode, as opposed to emitting into the free space. And so it turns out for waveguides, that simple waveguide, that's not very high. So you end up maybe emitting a lot of light into free space. So collection efficiency goes down. The way around this is to make so-called photonic crystal waveguides, or broadly speaking, slow light waveguides that have increased density of optical modes. So density of optical modes is proportional to 1 over group velocity, and we talked about the group velocity at the beginning. So you need to have very flat dispersion, and then actually the density of optical states that the mirror can couple into is very, very large. And then basically quantum dot in such a waveguide, photonic crystal waveguide, can couple quite nicely, and you can make extremely efficient and bright source of photons. So there's a very nice work done in Peter Lodal's group in Denmark. They even have startup, I think, that's commercializing this technology. So that's one of the very nice ways of doing it. But people have done really well with quantum dots in 3.5 nanowires, 3.5 waveguides, of course, 3.5 cavities, and whatnot. So that's plenty answer. Back to you.
Okay. That's about time for the poll. Let me share the results. There's no right answer for this. It's just kind of to see what people's considerations are. It looks like a pretty even split. There are a few people who say neither. Neither's an interesting one because there's some arguments that you maybe don't even need your detector to be integrated. You can integrate everything else and then treat the detectors as a very expensive resource that you only have at like hubs or whatever. So that's an interesting answer. And then SPAT, I don't know, APD is 1 compared to SNSPD, which cool. Which a little bit surprising to me because I've only used SNSPDs and they're really nice compared to when I used SPADs in my undergrad. But
what about a wavelength? Did you I had to step out for a moment. Did you talk about a wavelength for SPADs, or how did
yes.
And
Yeah,
how people go around this? Maybe that's a good question. I don't know how we get feedback, but
I didn't actually talk about how to get around the wave. Oh, yeah. How to get the with SPADs, the most high performing ones are in silicon, which are operating invisible. Your telecom ones are InGaAs, indium phosphide, and germanium. We're still on that slide actually. Those actually have lower efficiencies. And one of the ways that we can actually get around it is that when you have your telecom band photon coming in through a fiber and arriving and you need to detect it, you actually upconvert it back up to visible in order to detect it. And that's something actually you can do with Kai2 nonlinear optics. So the same kind of devices brought to you by the same kind of devices that gave you spontaneous parametric down conversion, you can also do things like some frequency generation to upconvert it. Yeah, that's my spiel about that. Was that what you were looking for, Marko?
Yep.
Yeah, cool. Lower temperature, so less useful. Yep, that's a valid priority. And then yeah, so it looks like room temperature operation is still quite important to a fair number of people. So yeah, this was interesting, and I hope this helped you get a sense of what other folks are thinking. Well, other folks self-selected to attend this seminar. I know if you're working on research in a field, you can like get tunnel vision on a particular thing. It's always good to recontextualize. So now I will actually, well, let's just blast to, well, there isn't much to conclude. So yeah, so basically the conclusion is there are a bunch of additional circuit components we actually didn't cover. One of this that kept coming up is that sometimes you need to kind of convert particular frequencies by quite a large amount, like from visible to telecom or vice versa. So let's say you insist on using quantum dots or existing mature kind of color center vacancies. You have to somehow convert from like below 1 micron to 1550, and that's something you'll need a difference frequency generation for. And then if you insist on using silicon APDs, for instance, then you'll need to convert telecom to visible, and that means you need some frequency conversion to convert 1550 back up. Those are two things that are brought to you by the same devices that give you spontaneous parametric down conversion. So yeah, so I think that that maybe is a partial answer to one of the questions I have here, which is does this mean we better focus on heralding systems and probabilistic sources more than others? This partial answer to this is, well, just in terms of like a quality of a single photon source, I think it's kind of debatable. But from the fact that, you know, these you actually kind of get for free a lot of additional functionality that isn't otherwise supported, such as large wavelength conversion across like hundreds of terahertz. If you can kind of develop those, it's actually really useful in other ways. I think if you were at the talk yesterday about hardware network, the whole time we were assuming that, yeah, you can't shift the frequency. Well, you can't shift the frequency yet. It's my opinion, but that's if you can guess what I spend my day-to-day thinking about a lot. This should probably give you a clue. Yeah, so I think that question was answered. And then so in summary, you have a kind of a whole zoo of material platforms, and you know they each have their strengths and weaknesses. You have ones that, you know, are really, really low loss, but maybe like don't have that much functionality for active devices or the devices that you need for quantum photonics, such as silicon nitride and in by certain definitions silica. In reality, like for those, really the best devices that you can make there are like things that require low loss. But in terms of like the sources that you require, sources and detectors for quantum information processing, you're kind of not doing great if you just want to use that material, unless you want to, except for the you making a probabilistic single photon source. 3.5 is really nice. It has probably the most amount of active device and that can be monolithically integrated. And the fabrication is not terribly out there. But the downside is its loss is high-ish. We can also see that from the fact that, you know, when they say low loss, you're actually comparing it to, they're actually comparing with silicon, which, as Marko talked about way earlier, silicon is regarded as fairly high loss to begin with. And then we touched briefly on diamond. I'm just gonna be pedantic here, and Marko, please disagree with me if you would like. That diamond's a nanophotonic platform, but not quite integrated photonics, because it's still at the level of individual devices. You're not like cascading them a bunch yet. You don't have system depth. And there's no clear path towards like if you can scale up production like on wafers very quickly. So that's my take on diamond as a potential.
Maybe can I maybe also add a few thoughts in the end?
Yeah, sure.
Like one of the things, like that's certainly correct. At the same time, my favorite thing to say is that I do not anticipate quantum computers and quantum repeaters being sold in Best Buy just quite yet. So maybe having a handful of diamond quantum memory strategically placed on some backbone made of, let's say, lithium niobate or aluminum nitride or something like that is actually good. You know, it can scale in that sense that you can actually integrate diamond thin films in particular with other platforms. I think that's actually quite promising direction. Another thing that people like, this is maybe more like just a broad comment, and other people that in photonics in particular often get stuck on this is, oh, but is this platform a CMOS compatible or not? And what I like, a lot of these platforms we discussed, that there are features of quantum are not CMOS compatible, and then people often are quick to dismiss them. And I think this is very wrong, because actually there's many other scalable photonic technologies that are not CMOS compatible and just alive and well, like 3.5 semiconductors, or I mean they're actually being introduced now as CMOS foundries, or but you know, like lithium niobate based devices, like surface acoustic bases, stuff like that. So actually scalability means different things, right? In different communities and different technologies. But photonics broadly, I would say photonics backbone with decorated with various materials for laser sources, for detectors, for memories, I think is scalable enough. Let's go with that to realize the interconnects. So yeah.
Yeah, I think then I guess to summarize maybe or rephrase what you said, like I think for a reasonable like photonics kind of platform for something that's useful, it will probably needs to be some genre of like hybrid or heterogeneously integrated thing. I always mix those two up, but that's what you meant by decorating, right?
There's actually some nice questions percolating. So Brianna, feel free to cut us off. You're already like, but that's so much fun. At first I thought
Yeah.
3 hours is too long, but it's too short. But maybe, okay, Raman scattering is very important for frequency conversion in particular. And CJ may have mentioned this in passing that, we need to strategically choose the process so that Raman noise is kind of right, like further onto red shifted from photons that we are interested in, not to pollute single photons. So this is actually a really important question. And ferroelectrics do not have high loss associated with them. Lithium niobate, thin film lithium niobate is one of the lowest loss photonics platform demonstrated, only second to silicon nitride. Barium titanate is a little higher loss, actually much higher loss at the moment. But I think it's a matter of improving growth capability, which is done in CQN by Julia Mundy, for example, as well as fabrication, something we and others are doing. I think that's probably going to go away, this kind of increased loss. But lithium niobate is ready to go, pretty much.
There's a question about radiation tolerance of single photon sources and relative sources and detectors. I wonder if I'm not clear what this means, but I wonder if it's kind of a mismatch between the rates of the brightness of single photon sources and detectors.
No, I was just, I think
Right?
radiation, space, like when we satellite the ground,
Oh,
communication. Yeah.
okay.
And certainly people are thinking to put sources, photon pair sources in satellites and detectors as well. So I wouldn't, I wouldn't say this is a consideration for sure, is being considered. Yeah.
And then there's some specific questions about parts of the heralded single photon stuff. So let me back up a lot actually. Yeah. Does the answer to the poll depend on whether you're using a photon number resolving detector or not? I'm actually not sure which one refers to. So if you still have that question, if you would like to send along another one to clarify which poll, that would be great. Option 3.
TJ, maybe we can
Option
provide
2.
the email addresses if people want to. I think Brianna, right? We
Yeah.
had time, right? Are we, Brianna?
Yeah, you are. We can add them to your to the chat if you'd like to. Otherwise I think now's a good time to wrap it up, and if people want to converse over email, that's fine.
Yeah. Can everyone see the chat?
Yes, if you chat out to everyone, then everyone can see.
Sure. So let me then in that case I'll just drop my email and then you can bounce out.